circular. An almost circular figure could be a little bit elliptical, or it could be circular with a little blip on it, or little square on it, and you don't know how to really, what do you mean by almost circular? Whereas circularity, you can give a simple definition, in a mathematical definition. So that was the difficulty of characterizing Mach theta functions. So to just to get you started, let's remind ourselves what are modular forms, because we will need to understand these notions precisely. So a modular form f tau of weight k on SL2Z group is a holomorphic function on the upper half plane that transforms in this particular manner. So basically it's invariant up to this factor of c tau plus d to the power minus k under SL2Z matrices, which are just 2 by 2 matrices of integers with determinant 1. So S means special linear transformations. And in particular, f tau plus 1 is f of tau. So you can do a Fourier expansion in, and you can write f tau as a n q to the power n, where q is exponential of 2 pi I tau. So this is sometimes called the Fourier expansion or the q expansion of the function. Now, why do physicists worry about this modularity? Because modularity comes in physics in many contexts. Basically, the SL2Z group appears as a physical symmetry in many different contexts. And therefore, the physical observable should exhibit that symmetry. And that's how modularity becomes important. So in holography, if you think of ADS-3 quantum gravity, then ADS-3, Euclidean ADS-3, as you know, is a solid cylinder. So it's solid cylinder. And its boundary of this manifold is a torus. Now, if you identify this and this is identified. So you take a solid cylinder and identify the two ends, then it becomes that is Euclidean ADS-3, thermal Euclidean ADS-3 with this identification, and the boundary is a 2 torus. And because in ADS-3 what is really important is just the conformal symmetry, what is important is the complex structure of the torus, and there is a tau parameter of the torus. And that is the tau parameter that we encountered earlier. And so in this context, it appears in this manner. In duality, for a 4-dimensional quantum gauge theory, a congruent subgroup of SL2Z is an S duality group. And there the tau parameter is basically the coupling constant. So tau is like 4 pi, the axion field plus I times the theta parameter plus basically it's 1 upon g square, 4 pi I divided by g square, where g square is the coupling constant. And in topology, which may be more familiar to you, in generally you must have encountered this. In 2-dimensional conformal field theory, if you consider the partition function of a conformal field theory on the torus, then SL2Z is the mapping class group, which is the group of diffeomorphisms modulo while which are not continuously connected to identity. So in physical observables in all these 3 physical contexts are expected to exhibit modular behavior. And so that's why modular symmetry appears in physics. And not only is, it's some symmetry, but it's actually a very powerful symmetry, because modular forms are highly symmetric functions. And one particularly powerful theorem is that the ring of modular forms is generated by just 2 functions, which are called the Eisenstein series. And I have given the explicit expression for the Eisenstein series in my lecture notes. You can look at it, and the Q expansion. So E4 of tau and E6 of tau. E4 is a modular form of weight 4, and E6 is a modular form of weight 6. For example, for a weight 12 form, if you want a weight 12 form, what do you mean by ring? Ring means that you can add these modular forms and the weights add. And if you multiply the modular forms, the weights also, if you add the modular forms, the weight remains the same. You get them another modular form of the same weight. And if you multiply 2 modular forms, you get a modular form whose weight is the sum of the 2 weights of the 2 modular forms you have multiplied. So for example, so you just take all such monomials and you can take any linear combination you like. So for example, if you want a weight 12 form, then the only 2 possibilities are E4 cube, according to this theorem, and E6 square. So any weight 12 holomorphic modular form has to be of this form, and therefore you see that it has only two complex numbers which remain to be determined, a and b. And so if you know a first few Fourier coefficients, q coefficients, then you can completely determine this, because you know the q expansion on the left hand side. The q expansion of E4 and E6 is well known. So you just compare this equation and you can figure out all the ANs in terms of A. Once you figure out AB, then you have figured out all the ANs. So that should give you some idea about the power, because if you take a generic function, if you want to specify a generic function, you have to specify infinite number of Fourier coefficients. Why somebody is sharing it? People are being allowed to share their screen. That should be stopped somehow. Somebody is sharing in the middle. He should not be sharing this. Whoever is trying to do that, please stop doing it.
I think nobody except co-hosts should be allowed.
But it was somebody, Fawad, somebody was sharing it. Okay. So because of that, instead of knowing infinite number of Fourier coefficients, you just need to know the first two Fourier coefficients, and then you have completely determined the function. And in fact, I learned from my distinguished colleague Zagier, who's a little bit like a modern day Ramanujan. This is the trick behind many of these very magical identities that people like Ramanujan wrote down, which would look completely miraculous to you, because the left-hand side doesn't look anything like the right-hand side. But if you know secretly that both sides have a modular symmetry, then all that you have to do is just check that the first few Fourier coefficients are the same, and then you have proved a magical identity. Another very important, so far we have only used the tau going to tau plus 1 symmetry, but there is a very important part of the symmetry which is tau going to minus 1 upon tau, which in the gauge theory context is the G going to 1 upon G, strong weak coupling duality. Or in the case of conformal field theory, it takes the high temperature limit of the theory to the low temperature limit of the theory. And this leads to what you might recall is called the Cardy formula in conformal field theory. And it's more exact, it's exact generalization known as the Hardy-Ramanujan Rademacher expansion. So all that follows, and therefore, that's the reason why modular forms have proved to be very useful in physics. So now let's come to mock modular forms. The mock modular form, the definition is a little bit more complicated. You don't have just one function. So the function f is what you want to call as the mock modular form. But to specify that mock modular form, you actually need to specify another function g, which is called a shadow. So a mock modular form is actually specified by a pair of functions, f and g, where f tau is a holomorphic function on the upper half plane with at most, the growth properties are such that it doesn't grow too rapidly at tau going to I infinity or q going to 0. At all cusps, those are called the cusps of the cusps. And g tau is a holomorphic modular form of weight 2 minus k, such that f hat, which is a sum of f tau plus g star, and I will tell you what is g star, it's some function constructed out of g of tau. If you take this particular combination, then it transforms like a holomorphic modular form of half integer weight k for some congruent subgroup of SL to Z. So this was the definition given by Zwegers and by Zagier, elaborated by Zagier. So the important point to note is that f is the function of Ramanujan, for example, is what you would call is a mock modular form. It is holomorphic, but it has no obvious modular properties. G is called its shadow. It's both holomorphic and modular, but by itself it doesn't completely determine f. And f hat is called as modular completion, which has nice modular properties, but it is not holomorphic. So this kind of incompatibility between holomorphy and modularity is the essence of mock modularity. So basically, it's like an exclusive OR. You can either have holomorphy, or you can have, or exclusively you can have modularity, but you cannot have both. So the function f is holomorphic but not modular. The function f hat is modular but not holomorphic. And this, as I said, this incompatibility is the essence of mock modularity. Are there any questions at this point? You can raise your hand if you have. I think the person who shared was Fadwa Ben Abdallah. For some reason, his screen showed. Okay, so please make sure that it doesn't happen again. Do you have any questions?
I don't have any. I haven't received any questions. Well, about the lecture in the chat.
Okay. There is.
I don't see any.
I see one chat.
Okay,
very good. Yeah, so feel free to raise your hand, ask a question, so that we would like to make it interactive. So and it's an experiment for us also, how to run this kind of a school. Okay, so another way to characterize this lack of holomorphy is to look at this function f hat rather than looking at the mock modular form itself. You can look at the modular completion, what we call the modular completion f hat, and this will also allow me to explain to you what is G star. So a modular completion of a mock modular form is this function f hat, which is not holomorphic, but it transforms nicely under modular transformation with some weight k, following the definition I had given you before. And it's related to the shadow. You can recover from it the shadow by this following holomorphic anomaly equation. So normally, if you took a holomorphic modular form and it took its tau bar derivative, you would have gotten 0. But here, if you take the tau bar derivative, you don't get 0, but up to these factors of tau 2 to the power k. Tau 2, so tau is basically tau. Sorry, what is happening?
Atish, there is actually one question in the chat if you want.
Yes.
So there's a question from Shivnak Sister. The question, but isn't G both holomorphic and modular? What exactly is the incompatibility? Maybe you can clarify if there is some confusion.
G, no, what is the question?
It's a question in the chat.
Yeah, G is both holomorphic and modular, but the object of interest, the mock theta function that Ramanujan wrote down was not G, but just F. In fact, that was part of the mystery. Ramanujan only told you what was F without telling you what is G, because he had some inspirational ideas. And that's why people took so much time to figure out. So without G, without knowing what is G, if I just give you F, you have no idea of verifying the modular symmetry, how to verify a modular symmetry. See, if I just give you a function, just look at that function that Ramanujan wrote down. How will you even verify? How will you even begin to verify that it has SL to Z symmetry? It's actually quite hard to do it. We sort of rely on all kinds of theorems and experience. So that's the incompatibility. Does that answer your question? Okay. So the shadow is both holomorphic and modular, but by itself does not determine the modular completion. The non-holomorphic correction G star by itself is not modular. The holomorphic mock modular form by itself is not modular. The completion f hat contains all the information, but it is not holomorphic. So that's the kind of incompatibility that we're talking about. Now, how do you construct G star given G? So G, as I told you, is a perfectly nice holomorphic modular form. So it has a Q expansion Bn Q to the power n. So given Bn, I can construct G star by this somewhat complicated looking formula. But don't be too alarmed by it. It's actually not such a complicated equation. Basically, what you want is that when you take a derivative of this with respect to tau bar, you should get G bar. G bar means Bn bar Q bar to the power n. And one nice function which does this, if you take the derivative of the error function, you'll pick up the right powers of exponents so that it will cancel everything. And you will be left with, consistent with this equation, on the right hand side, you'll be left with G bar of tau. So this you can take it as a little homework problem. You just act upon it with the operator, this operator, 4 pi tau 2 to the power k del by del tau bar on this. In some sense, this is the kernel of that equation. Okay, there are many ways of writing that kernel, and this is one way to write the kernel. That if you act upon it, you can make sure that you will get 2 pi G bar of tau, or 2 pi times Bn bar Qn to the power n, right? So when you act upon it with that operator, what you should get is 2 pi times bn bar q bar to the power n. Okay. Now this incomplete gamma function will make its appearance again. This is sort of kind of going to be the hero of our story. It will appear in the context of, it appears in the context of Atya Pathodi Singer index theorem. It appears when we do some supersymmetric quantum mechanics calculations. And that's going to be the link to physics of this mock modular story. So I think there is a kind of a nice geometric analogy to keep in mind. A mock modular form is a little, so if you ask me what is a modular form, I would say it's a little bit like a circle. It's a circle in that it's a function of high degree of symmetry, very much like that a circle is a geometric figure with a high degree of symmetry. Under SO2 rotations, it doesn't change its form, much like a modular form, which doesn't change its form under SL to Z transformations. And now the property of being holomorphic, you can liken it to the property of being blue. So you can ask, a holomorphic modular form is a little bit like a blue circular geometric figure. And a mock modular form is a little bit like this figure that I'm showing you. It is missing that little piece. And that little piece is not blue, it's not holomorphic. If you add that little piece, the figure starts looking circular, and therefore it has modular properties, but it is no longer blue. So there is an incompatibility between blueness and circularity. And that red little thing that I have to add is constructed out of another blue circle, little blue circle, which is our G. So you have to do something to it, you have to straighten it, there is some operation that you do, and you add that little piece there, and it fits perfectly. And then you get a modular form, a modular object. So that's the missing thing. That's Ramanujan somehow drew just this little blue arc on the left-hand side without telling you what to fit in there, that little red thing, and how to get it. And that's why it remained mysterious. So now there is another generalization that is interesting of modular forms, which are called Jacobi forms. And this is a function of two variables, and we will encounter this again in the physics application a lot. It's a holomorphic function of two variables in the upper half plane and the complex plane. And it's called a Jacobi form of weight k and index m if it is modular with respect to tau in the variable tau. And essentially it's elliptic, which essentially means doubly periodic in the z variable. And one way that you should think about this is think of the tau parameter as the tau parameter of this torus. And z is the coordinate of this torus. Okay, so in fact, you can obtain this torus from considering a lattice of points in the upper half plane. And you're modding out that, so not upper half plane, the complex plane. And you mod out that, the complex plane by this lattice. And that's how you can obtain torus. So the z is the coordinate in that complex plane. And clearly, z going to z plus lambda tau plus mu just takes you, it's like a lattice shift. So you want a function which is invariant, roughly invariant under this lattice shifts and roughly invariant under modular symmetry. So it has high degree of symmetry under modular symmetry. So that's what the first equation says, that up to a phase and this factor, it's basically invariant under modular symmetry. And it is roughly up to the phase, it's invariant under the lattice shifts. And therefore, again, it admits now a double Fourier expansion because it is invariant under z shifts as well as tau shifts. And you have a Fourier coefficients labeled by n and r, q to the n, y to the r. Sorry. Now, these Jacobi forms occur naturally as elliptic genera of a superconformal field theory. So elliptic genera is some mathematical terminology which has to do with some infinite tower of Dirac-like operators. This is called the elliptic genus. But in the context of superconformal field theory, it has a simpler physical definition, which may be more familiar to you. But consider a conformally invariant nonlinear sigma model with a target space X with 2, 2 superconformal symmetry. So a good example to keep in mind is in fact like a K3 surface. The target space is a 4-dimensional surface like K3, which actually has a 4, 4 superconformal symmetry, but in particular it has 2, 2. with left and right super Virasoro algebra. So Virasoro algebra you know, and super means that you just have super partners and you have some R symmetries, U1 R. So the super Virasoro algebra has some U1 R, sorry, U1 left. So what am I saying? U1 left plus U1 R symmetry. And F left and F right are the charges of those symmetry. So you can construct a partition function. If you forget about these factors depending on F right and F left, then what it is essentially computing is Q to the power L naught and Q bar to the power L naught bar, right? This is the partition function that you would normally compute in conformal field theory. But here you insert this -1 to the F right plus F left and e to the pi 2 pi I z F left. And this is called the elliptic genus. And it is related to the topological properties of this manifold X. So there is a connection to the mathematics through this manifold target space X. But you can define it entirely within conformal field theory. And this elliptic genus defined in this manner is a Jacobi form. So to see this, maybe we can discuss this in the tutorial. By conformal symmetry, it's kind of more or less obvious that the path integral has to be modular. The reason is that for a path integral, you can always regulate it. If you have a diffeomorphism invariant theory, if you regulate it using a diffeomorphism invariant regulator like a heat kernel or something, then the path integral is diff invariant. And because it's a conformal theory, it means it's also while invariant. And as we saw, modularity is basically, modular symmetry is basically diff mod while. So it has to be modular invariant. And then there is a spectral flow symmetry, which has to do with the fact that this U1 current algebras on the left and right, you can bosonize. And the shifts of that boson can be basically identified with the spectral flow symmetry. But there are many, basically spectral flow symmetry is the symmetry of this algebra. And that corresponds exactly to the shifts that we are talking about, the elliptic properties that we are talking about. Okay, and another way to think about it is that it's like a right moving Witten index. So you have a conformal field theory, the left movers and right movers more or less don't talk to each other. And the right moving theory, as you saw, for the right moving theory, there is no insertion. The insertion here is only this function, which depends on the left moving charge. For the right movers, you only have -1 to the F right. And -1 to the F times Q to the power the Hamiltonian, or Q bar to the power the Hamiltonian, is basically the Witten index of the right moving theory. And by an argument, a general argument about Witten indices, it depends only on the number of ground states of the theory. It basically counts the indexed, the positive fermion number ground states minus the negative fermion number ground states. So F right and F left, because they act only on the fermions of the theory, they can be identified with the fermionic charge. So if F right is 0 mod 2, then it's a boson. And if it is 1 mod 2, then it's a fermion. And therefore, this I will come to in the next lecture perhaps. Okay, so anyway, using these two properties, you can see that the elliptic genus has to be a Jacobi form.
Atish?
Yes.
There are a couple of questions in the chat.
Okay.
If you so one question is from Arif Moht. So the question is the following: there is also SL to the action on three-dimensional conformal field series with U1 global symmetry. This is related to electromagnetic duality in the bulk ADS if the series is holographic. I'm wondering if it has any connection with mock modular forms.
Well, first of all, you will understand that, okay, first of all, it will surely have something to do with modular forms. And when the modular becomes mock, as we will see, there is a particularly good physical understanding now. I mean, when I started to work on this, it was not clear at all. But it will become clear. And I'm quite sure that there would be context in this situation also, where mock modular forms will come to play a role.
Okay, there's another question from Mohammed Al-Fiki. Is G unique? So I guess G is what you call the shadow. Maybe you can comment.
Yes, G is determined by, I mean, F and G have to live together. And they are determined by each other. You can add, F is not unique because you can add anything to F without, spoiling the modular properties. You can add to it any other ordinary holomorphic modular form, and it will not change the holomorphic anomaly equation. So it's more like F is not unique, but G is unique.
There also one question from YouTube.
Yes.
So chi counts the number of right moving ground states and is also a property of the manifold?
Yes, it's also a property of the manifold, and that property is known as the elliptic genus of that manifold, and it calculates the index of some infinite family of Dirac operators.
Okay, thanks. That's it.
Okay.
Sorry, you lost again.
Yeah, okay. So I'm going a bit slow, so I'm going to speed up a bit, or since there were questions, maybe I can. Okay, so two examples are this. I don't know, you're all familiar with the Jacobi theta function. So one simple example is this function A of tau, theta 1 square divided by eta to the 6. So eta is the Dedekind eta function. And I don't know, you'll have to brush up on your Jacobi theta functions. These are some Jacobi theta functions you might have encountered when you did, say, the path integrals for fermions or the partition functions of fermions. So there are 4 Jacobi theta functions: theta 1, theta 2, theta 3, theta 4. Theta 1 vanishes at z. This is called the odd theta function, and the other ones don't vanish at z. Theta 2, theta 3, theta 4. And two very well-known examples are A tau of z and beta of z. And roughly speaking, actually, this product might look a bit strange to you. I mean, sorry, if you're not familiar with, actually, A tau of z actually has a very simple A tau of z is roughly of this form up to some factors. So roughly speaking, you can recognize the numerator are basically 4 fermions divided by 4 bosons. It's a partition function of 4 fermions and 4 bosons. And that's basically the partition function of a T4. If you take a 4 torus, then it has 4 bosonic coordinates. And if you have supersymmetry, then it has 4 fermionic coordinates. And this partition function, this modified elliptic genus that is called, is nothing but, and it's a Jacobi form of weight -2 and index 1. And if you can now, from this, you can follow the definition of theta 1 and eta 6, you basically get the function I wrote down. Other one is the elliptic genus of K3, which has this other theta functions, theta 2 square tau z divided by theta 2 square of tau, etc. This sum, and it has the property that b of tau z is equal to 0 is 24. Because you can see, if you put z is equal to 0 in this equation, you will get 8 times 1 plus 1 plus 1, which is 24. And that is nothing but the Euler character of K3. So the elliptic genus, somebody asked this question, is this a property of the manifold? Yes, indeed, it is a property of the manifold. And it has some topological information about the manifold. In particular, if you evaluate it at z is equal to 0, you get the Euler character of the manifold. And for other values of z, I mean, other Fourier coefficients will give you other more detailed information about the topology of this manifold. Okay. Now, why do I write down? So of course, T4 and K3 is something that these are the 4 manifolds that you're familiar with, and they come very naturally as, but there is also another powerful theorem that the ring of Jacobi forms is again generated by A tau and B tau of Z. So just like the ring of modular form was generated by 2 functions, the ring of Jacobi forms is also generated by 2 functions. But now the coefficients can themselves be modular forms. So for example, if you want a weight 4 index 2 Jacobi form, then index 2 means there are only 2 possibilities. Once again, index and weight also add when you multiply. So if you want index 2, there are only 3 possibilities: a square, b square, or ab. But they have different weights. So a square has weight -4. And if you want something of weight 4, then you have to multiply it by e4 square. AB has weight minus 2, so you multiply it by E6. And B square has a weight 0, so you multiply by E4. So that's all. This is very powerful again. Without doing any calculation, sort of, you can, without lifting your finger, so to speak, you can sometimes do very difficult calculations. So for example, elliptic genus of K3 is equal to B. And you know that how? Because the elliptic genus of K3 has to be an index 1 weight 0 form, Jacobi form, and there is only one, namely B. And we have chosen the normalization such that, in fact, elliptic genus is exactly equal to B. We could have chosen a different normalization. Another important property is that using the elliptic property meaning symmetry under shifts of Z, you can basically expand this any Jacobi form in terms of ordinary theta function. Another way to say that is you can basically take out the entire Z dependence in terms of some standard level m theta functions defined below. They are just some powers of q to the power something, basically Gaussians of q and y to the power something. And then you are left with a vector HL of tau, a vector of modular forms. So by this theorem, this is the theorem of Eichler and Zagier, that a Jacobi form of weight k and index m is equivalent to a vector valued modular form of weight k minus half. So you could do it either way. Instead of specifying a Jacobi form, you could just specify a vector HL of tau, where L going from 0 to 2m, h going from 1 to 2m. It is a 2m component vector of weight k minus half. Because the theta functions have weight half, so h has to have weight k minus half. So okay, so these are all the definitions that you will need in my talk. Now let's come to physics. And one very inspiring quote is this nice quote of Freeman Dyson. It's from his very nice talk. I recommend you. There's a very nice look on the internet, a walk through Ramanujan's garden. This was a talk that he gave at the 1987 Ramanujan Centenary Conference, which says that my dream is that I will live to see the day when our young physicists, struggling to bring the predictions of superstring theory into correspondence with the facts of nature, will be led to enlarge their analytic machinery to include not only theta functions, but Mach theta functions. And I have to say, I was young in those days. And Ramanujan is an inspirational figure for people from India, for somebody like me. But I never thought that actually I will ever in my research will use this, I will be forced to use these Mach theta functions. But so even though it is not really to bring predictions of superstring theory with the facts of nature, we will see that they come up in some very important concepts like holography and duality, which are quite central to, which are making a big appearance in not just in string theory, but in physics as a whole. And so it's actually, it was a prescient remark that. So how did I get into this? There was a puzzle with black holes that led me to this. So if you look at some counting function, so as you know, the degeneracies of black holes, quantum degeneracies of black holes because of the Bekenstein-Hawking formula and Boltzmann relation tells you something fundamental about the degrees of freedom of quantum gravity. So it's a quantity of great interest for anybody who is interested in quantum gravity. And now, starting with the work of Strominger and Waffa, we have been studying this black hole entropy, but actually now it has become possible in the recent years through work of various people, including myself and collaborators, to really study quantum corrections to the black hole entropy and to really study the integer that comes out of corresponds to the number of degeneracies of states. So a full quantum generalization of the Bekenstein-Hawking formula you can study now. And for that, you need to know the degeneracies of quarter BPS black holes. And one particular simple context is type 2 compact Different K3 cross T2. And the counting function is a meromorphic Jacobi form. You see, it's a meromorphic in the tau z variable. So look at the function. A tau of z, which you saw, has a double 0, is now appearing in the instead of numerator, it's appearing in the denominator. Therefore, this function has a double 0. And the quantum degeneracies are claimed to be given by the Fourier coefficients of this counting function. However, given the double pole, the Fourier coefficients would depend on which contour you choose, because if you cross the pole, then the answer will change. There will be a residue that will pick up. So what is wrong with the counting? Did people do something wrong in their counting? Because black holes should have unique degeneracies. So there is another puzzle with instantons which Pavel will talk about. If you consider what is known as the Waffa-Witten partition function of n equal to 4 four-dimensional supersymmetric gauge theories on manifolds like CP2 with some gauge groups like garden variety gauge groups like SO3, and the coupling constant is this tau parameter that I told you, then by some very general argument, you expect that Z of tau should be tau bar independent. But it turns out, and it should also be S duality invariant. But it turns out there is no such object which is both holomorphic and has a nice duality properties. There is an object which is natural, whose holomorphic part looks nice, and which has the nice duality properties, but it is not holomorphic. So once again, you are led to some kind of a holomorphic anomaly. So, or you have to give up duality. So the question becomes, what is wrong with duality? And there is a puzzle with elliptic genus. If you now compute the elliptic genus of some sigma model, say like whose target space is K3, a compact manifold, then again you get elliptic genus which is holomorphic by the general arguments. This Witten's argument that I told you, that the Witten index has to be tau bar independent. The right moving Witten index has to be independent of the temperature. But for non-compact SCFT, a sigma model with infinite cigar, like for example, if you take an infinite cigar, you take a cigar-like geometry, infinite cigar-like geometry. For example, the Schwarzschild black hole, Euclidean Schwarzschild black hole, if you remember, in the RT plane is like a cigar. So if you take an infinite cigar, then the elliptic genus is no longer holomorphic. If you insist on holomorphic, it's no longer modular. So something is going wrong with conformal invariance. So what is wrong with conformal invariance? So in all these three cases, the answer involves mock modularity from the mathematical point of view and a non-compact path integral from the physical point of view. So this might answer the question that somebody asked, that can mock modular forms appear in that case? So answer is yes, if the path integral has some non-compact contributions. And this is the point that we will try to understand in the next lecture. But now, how much time do I have, Pavel?
Well, you have in principle, well, in principle it's up to 2 p.m., but well, it's supposed to include some
questions,
some question time.
Okay, good. So let me try to bring this to some logical point. Maybe I will take 7-8 minutes up to, and then we can have questions. So let's first understand the connection of mock modularity with holography. This was the first avatar that I was going to tell you about in the context of black hole counting. So as I told you, in the context of black hole counting, the puzzle was that the counting function doesn't seem to give rise to well-defined degeneracies. What is going on? A black hole should have well-defined degeneracies. And the answer turns out to do with something known as the wall crossing phenomena. The wall crossing phenomena is the follows. If you take a theory like K3 cross T2, compactified theory, and take type 2 theory, compactified and some manifold like K3 cross T2, then depending on the size and shape of the K3 and T2, you could have a big K3 or a small K3 or a torus which is a bit twisted and so on. There are actually lots of, as you know, there is a Narayan moduli space. There are a large number of moduli of this theory, depending on the shape and size of K3 cross T2. And depending on where you are in this moduli space, so moduli space is not your physical space, but depending on where you are in this moduli space, the moduli space is sort of split up into walls. So this is your moduli space. And depending on what are the values of moduli, you have some degeneracy here and a different degeneracy over here. Okay, I cannot change the color so easily. Okay. And so when you cross the wall, so you have some different degeneracy over here. And there is a wall, which is a codimension 1 surface in the moduli space. So you have some large, let's say 80-dimensional moduli space, and there is a 79-dimensional wall in the moduli space. And if you go, as you cross the wall, the number of BPS states actually jumps. And so the whole moduli space split up into chambers separated by walls. And in fact, now there is a very nice understanding that the poles are related to walls, and the residue at the pole is related to this jump in degeneracy. So there is no surprise, because indeed the degeneracies of BPS states in this context is supposed to jump. But then that would be strange, because if you want to identify this BPS state with a black hole, the quantum degeneracy of a black hole is supposed to be a property of only its horizon. I mean, that's the reason why somebody like me is interested in black holes, is because the horizon of the black hole is telling you something about the short distance degrees of freedom of of quantum gravity. It's not. So how can such a very fundamental quantity having to do with Planck scale physics depend on where you are in the modular space? It should not depend on the asymptotic moduli. And the answer turns out to be this, that indeed the number of states of a black hole of a given horizon are in fact depend only on the horizon of the black hole. They don't depend on the rest of the junk. But what happens is that on one side of the wall, you only have a single black hole, single centered black hole. But on the other side of the wall, it can happen that two black holes can actually form a bound state. And the distance between those, so they contribute to the index on the right hand side, but they don't contribute to the index on the left hand side. And the distance between them, even though the horizon degrees of freedom don't depend on the moduli, the distance in the bounds between this bound state, the distance between the two centers of the bound state, do depend on the moduli, and it sort of goes to infinity as you approach the wall, and this state drops out of your spectrum, and that's how the degeneracy jumps. So that raises another puzzle, that what is, I mean, after all, this multi-centered black holes is some junk. I'm not interested in them. How can I remove them and separate them and just talk about the horizon degrees of freedom? And that's the question that actually led me to this collaboration with Murthy and Zagier. You know, this was a question that I asked Zagier. He's a well-known number theorist. So this is a kind of an interesting example of cross-cultural collaborations, because the culture of number theory is very different from physics. And I thought, okay, there is some meromorphics, there is some pole. We were just talking about it in a cafe, you know, over some coffee. And I said, okay, how do we deal with this pole in the Fourier coefficients? And I thought the answer would be simple, but he said, no, this is a very difficult problem. Goes back to Ramanujan. And my former graduate student, which was Vegas, he has just only recently solved this problem. This was an open problem for the last so many years. And then we started to collaborate on this. And I thought, okay, with the help from somebody like him, we'll probably figure it out quickly, but it took a number of years. And one of the results that we arrived at is actually has a very nice physical motivation, is this decomposition theorem, that there is a unique decomposition of this counting function between a polar part and a finite part. The polar part is related to what is known as the Apple-Lurk sum. And it has exactly the same poles in Z as the original counting function that you're looking at. And the finite part is free of poles. And therefore, its Fourier coefficients are uniquely defined without any ambiguity. And that's the answer to my question, what counts the degrees of freedom of the single central black hole? Is the function psi m finite? So this is the nice interpretation, that the polar part counts the microstates of multi-central black holes. The finite part, psi m f, counts the microstates of a single central black hole, which is indeed a property only of the horizon. The sum actually contributes, counts the number of states available at asymptotic infinity, which includes everything that is inside, including single-centered and multi-centered black holes. And the non-trivial part of the theorem, of course, is that you can take any function and divide it into two functions. That you can always do. But the non-trivial part of the theorem is that both of these terms admit a modular completion. And to understand that, I will just very quickly explain this Apple-Lurk sum. The Apple-Lurk sum is, roughly speaking, see the function, the original function, as I told you, a tau of z had a pole. So a tau of z went as 1 upon z square. Sorry. It went as z square. Okay, let me now. Sorry, my function psi m went as 1 upon z square at z is equal to 0. And therefore, it has a pole at z is equal to 0. But because its elliptic function is doubly periodic, it has poles at all the lattice points, lattice images of z is equal to 0. So it has an infinite number of poles in the complex plane like that. So what you can do is that, and it goes like that with some residue, which is P24m plus 1, which is some number, and eta 24 to the tau, which doesn't depend on. So with some number, we will remove that number and we will take that function 1 upon z square, and we take this average. It's sort of the method of images, that you sort of add over all the images of 1 upon z square, but with an appropriate phase factors, so that it has exactly the same properties, elliptic properties, like a Jacobi form. The Apple-Lurk sum has elliptic symmetry like a Jacobi form of index m and weight 2, but it has no modular symmetry. Similarly, you can remove this overall factor from your finite part, and then you're left with this function phi 2m of tau z. And phi 2m of tau z is what is known as the mock Jacobi form. This is the definition I had introduced earlier. And therefore, it admits a modular completion, which we denote by the hat. And one can similarly define a modular completion of a hat. So that's the non-trivial part of this theorem of that we prove, the decomposition theorem, together with Murthy and Zagier, that the counting function of single-centered black holes, which is basically related to this function psi f up to this overall factor, can be completed using, it has a modular completion such that this object phi hat transform nicely under modular transformation. And this is a very important fact, because without modular symmetry, you basically cannot do any calculations. You cannot even use Cardy's formula. You cannot figure out the asymptotic growth of states. So all this very powerful technology that we are very used to is immediately lost if you don't have modular symmetry. So this was very important physical consequence, that it restores to you the physical symmetry that was important to you. And moreover, just on physical grounds, since ADS3 boundary must have SL to Z symmetry, this is the natural object to identify with the elliptic genus of the boundary theory. And as I told you, a mock Jacobi form is the object that is very similar to the Jacobi forms, except that you use the theta expansion, and these functions HL now, instead of being modular forms of weight k minus half, are mock modular forms of weight. So in our particular case, phi has weight 2, so HL are mock modular forms of weight 3/2, and they admit some particular completion. And here is the holomorphic anomaly equation. Their shadow is given by this very nice theta function. So you can write the holomorphic anomaly equation for a mock Jacobi form in terms of this equation. It might look to you a bit complicated, but look, actually the right hand side is very nice. It's given entirely in terms of the theta functions of level m. These are very simple, nice objects with nice modular properties. So the shadow is particularly simple. It's not some very complicated, it's not a very complicated, in general, the definition allows you to have some complicated g of tau. But in this particular case, the g of tau is this just theta ml of tau. And there is this kind of this XOR property that I told you about, exclusive OR. And here, in the case of mock Jacobi forms, which are a two-variable generalization of mock modular forms, there is similar problem with this XOR property, that if you look at the meromorphic Jacobi form psi, then it is holomorphic in tau and z. I mean, it is meromorphic, but it doesn't depend on tau bar or z bar. It is holomorphic, but it is modular, but it has poles, and it's some complicated function. The mock Jacobi form phi that we talked about is holomorphic, but it is not modular, and it has no poles. It was free of poles. That's why we wanted to identify that with single-centered black hole degeneracies. The Apple-Lurk sum, which was basically an average of the single pole, 1 upon z square, is very simple to construct. You just take the pole and you take its elliptic average. And it is holomorphic, but it is not modular, and it has lots of poles. So its Fourier coefficients depend on which contour you use. And they actually, that's okay, because they count the number of degrees of freedom of multi-centered black holes. And those depends on which contour you are in, or which chamber of the moduli space you are in. And the completion of phi hat, whose holomorphic anomaly equation I just showed, is not holomorphic, it is not simple, but it is modular, and it is pole free. Okay, so I think I'll stop here.
Thank you. Yeah, we can. If you want, you can temporarily unmute yourself if you want to clap physically.
Yes, please clap. Please clap. It's a good. It's good motivation.
Okay, so yeah, there is a couple of questions in the chat. So first question is from Mohammed Numan Mutib. What does the modular completion correspond in the SCFT calculation?
Yes, so it is, as we will see, that is the topic of the next lecture. It is related to some contribution from, if you have a non-compact theory, suppose you have non-compact quantum mechanics, right? For example, like a hydrogen atom. As you know, hydrogen atom has bound states, but it also has scattering states, right? Because if you look at a hydrogen atom, suppose you have some quantum mechanical theory like a hydrogen atom. Sorry. Then it has some potential which say vanishes at infinity, the Coulomb potential. Then you can have some bound states which are here, but you can also have some scattering states. So in particular, as you know, you can have the spectrum can look something like that, the spectrum of the Hamiltonian. Just forget about super conformal field theory. Just take a non-compact quantum mechanical system. Non-compact quantum mechanical system will typically have a spectrum like that. And then there will be a continuum. And if you have supersymmetry, the usual argument is that if you have bosons, then they have a fermionic counterpart. But when you have a continuum, you cannot make that argument so easily because you cannot identify states one-to-one in that manner if you have a continuum. And in particular, the density of states for the bosons can be slightly different from the density of states for fermions. And that's really the essence of the mock modularity from the physical point of view. From the physical point of view, the completion has to do with the contributions from the scattering states, which is usually absent in the compact theory.
Okay, so there is another question from Bruno Carneiro. Could you explain again how you know that the poles are associated to multicentric black holes?
Yes, it's not at all obvious. There is a huge amount of work that has gone into it, and I've just given you the digested version of it. But the reason is that in this n equal to 4 compactifications, you know precisely the quarter BPS dions and the half BPS dions. And so this is a work done by myself and collaborators, then a group from Harvard and Gayatto and so on, and then a group from Harish Chandra, Ashok Sen and collaborators. So it has taken several years, actually, a number of years to figure out. But now we are, one can identify them. Basically, you can actually identify the states which it is which it is counting. And from that, you know that these are the multicentral black holes. In a general Calabi-Yau manifold, it's actually a very difficult problem. It's almost impossible to, it's a very difficult problem which has not yet been solved.
Okay, and another question from the chat from Jay Cushing. What is meant by simple in your table?
Yeah, it's not a particularly precise mathematical terminology. Simple is something like you take 1 upon z square, and then you're taking all its images, right? Roughly plus lambda tau or minus lambda tau minus mu, you sort of square. This is what you would have done. Suppose you wanted to take a pole 1 upon z square and you created kind of a doubly periodic function, then this is what you would have done. Basically, the upper Lug sum is something like that, except that you multiply with some phases, you know, q to the power this, y to the power that, just to make sure that it has the right properties, exactly the same properties that you see. Elliptic transformation had some very specific properties. Let me remind you. Sorry, I have to go back many. Here, you see, if you look at this, you want to pick up a phase. It's not exactly periodic. This kind of a phase you want to pick up. And so you sort of made this definition in such a way that you pick up the phase that you want. But roughly it's just an average of a simple pole, like, I mean, average of a double pole in this case, 1 upon z square. So in that sense, it is simple.
Okay, I don't see any more questions in the chat, and I don't see any raised hands. So yeah, so I guess we can thank Atish again.
Okay, thank you very much. So see you. I think we have a so just one point. I think we was going to have 2 tutors, but actually it turns out that they had some other engagements at the same time. So I will act as the tutor. I will be the tutor. So if you have any questions, we will go over them in the tutorial.
Actually, there is no. Oh, sorry, no, there's nothing. Okay, so we will resume in roughly 15 minutes at 2:15 by the next course by Ahmed Hamheri about quantum black holes.
Okay, ciao.
Hello.
Hi, hi.
Hey guys.
How are you?
Doing well. I couldn't catch the beginning of your talk, Atish, but whatever I caught was very nice.
Okay, thank you. Thank you. Yeah, I sort of figured out how to do this Blackboard kind of thing. This with iPad, it works quite nicely, actually. You use iPad as a Blackboard and it works nice. How are you to do it? On the Blackboard, the physical Blackboard?
Well, no, I wasn't going to use this. I have my lecture notes, which I hope you're not mad at me because they were handwritten and I just scanned them.
No. As long as there are lecture notes, I think that's good.
Yeah.
Hopefully, you'll put them in PDF one day. But
well, no. I mean, they're in PDF. That's what my slides are. Oh, you mean one day that I tech them up?
yes, okay.
Okay, we'll see.
Or we can get them teched for you or something like that.
Yeah.
No, but I think if they're legible, then it's fine.
Yeah. So you've been giving 20 minutes, then a short break, then another 20 minutes. Is that?
I sort of not exactly did that. I took a break. I mean, I asked for questions after 20 minutes.
I see. Okay.
I went for 45 minutes.
I mean, yeah, the idea is like whenever you find a property, you can stop to see if there is some sort of questions.
So I can just stop at natural points. I don't need to be.
Yeah, not precisely 20 minutes. Yeah, we didn't break the audience.
Okay.
And yeah, I will transfer the questions from the chat if they're written, or if there is some, or like in a particular break, if somebody wants to ask a question verbally, I will also.
I see. Okay.
Okay, good. So I will take a quick break and I will be back.
Sounds good.
In 10 minutes. So how are things in New Jersey otherwise?
Things are fine, considering everything. The IS is going to open on September 8th.
Ah, good. Open meaning fully, or you will be in some very controlled way, like we
in a controlled way.
way.
For example, take out lunches and also take out cookies.
but can everybody come? Like here, what we are doing is we are encouraging people to sort of come for 3 days, and
I see.
Not to make everybody land on the same day.
No, I don't know of any such restriction, but you have to get an approval.
Yeah, exactly. Yeah. So everybody has to get an approval, and so then the head of the section makes sure that not 2 people are on the same, and tries to avoid people being in the same. Like if postdocs are sharing an office, things like that. Students,
Yeah. So we don't have that.
You don't have that. Yes. Good. So, okay, good. I'll be back in 5 minutes. Just a short break. Yes. Okay.
Sounds good. Should I share my screen, Pavel?
Yes, please. You're allowed to, right?
Let's see. You see it?
Yes, I can see the whole screen.
You see everything? Okay. So if I
Yeah,
do
just in case, yeah, not just now it's full screen.
now it's just the PDF, right?
Yes, but there are a lot of kind of large margins. Now it's okay.
Better? Does it move smoothly when I go up and down? Is the connection good?
Well, for me, it's fine, I think. Yeah.
Okay, okay. Can you see my cursor, Pavel?
Yes.
Right.
So are you ready to start?
Yeah, I'm ready whenever.
Okay, so it's 2:15, and well, in Italy, and so we're happy to have Ahmed Almiri, and he will tell us about quantum black holes.
Okay, thanks, Pavel. So let me begin by thanking the organizers for setting up this really great school and for inviting me to give these lectures. And let me, I guess, begin by saying also, I hope that all the students, wherever you are, you're doing fine, you and your families. And thanks for tuning in. So these lectures are going to be about some quantum aspects of black holes, and with sort of the ultimate goal to review recent progress on the information paradox. This goal is, I guess, partly shared by these lectures and also by the lectures by Douglas Stanford after this one. So much of what we do in theoretical physics is often not actually studying the actual theory of the universe, but what we do is we consider toy models, models that we think capture sort of the essence of the physics that we want to understand. And in these talks, at least in my lectures, we're going to focus on a specific two-dimensional model of dilaton gravity of Jacobi Teitelbaums, known as JT gravity, coupled to a conformal CFT or conformal matter. The action for this model is the following. So it has two terms, the gravitational term, the JT action, plus the CFT term, where, as I said, the JT action is some dilaton gravity model as shown. Here, the first term is a topological term. You can show by, I guess, maybe the Gauss-Bonnet theorem or something. And the second term here is, which has sort of all the dynamics. It's a coupling between the dilaton phi and the Ricci scalar are constructed from the metric G. Okay, so this is the gravity action. There's also going to be a matter action, which is going to be a conformal field theory, which lives on the background metric G. Notice that the CFT does not couple to the dilaton. Okay, this is very essential. Okay, this is a theory with a boundary. That's why I have this boundary term here with the extrinsic curvature. And so you need to specify some boundary conditions. And so we put these fall-offs. The details are not that important for now. In this theory, something very special happens, which is that the metric localizes to ADS2. In the path integral, you could integrate over the dilaton along some contour, which is parallel to the imaginary phi axis, which localizes the metric to be ADS2 or constant negatively curved. So R has to be equal to -2. You can also derive Einstein's equations in this model by varying with respect to the metric. And you'll get an equation that looks something like this. There's some differential operator, which depends on ADS2, acting on phi, the dilaton. It's going to be sourced by the expectation value of the stress tensor from the CFT action. This is so even though the CFT was not coupled to the dilaton, Einstein's equations forces them to talk to one another. Okay. Let me see. Oops. Single page continuous. There you go. Okay. The solutions we want to consider for this theory are going to be vacuum solutions. These are solutions where the expectation value of t is equal to 0. And the claim is that all these solutions are eternal black holes. Here I've written the eternal black hole solution in 2 different coordinate systems. I'm not going to go through this in detail. You can look it up in your spare time. The only important thing is that you can express this black hole in so-called exterior coordinates that cover that separately cover the patches outside the black hole. So here and here. Here is going to be the sort of the Schwarzschild, it's like the Rindler time or like the Schwarzschild time. It's the time outside the black hole. And this is a static solution. The field phi only depends on sigma, the radial direction away from this bifurcation point. Okay. There are also Poincare coordinates that cover sort of a larger patch. And these are the usual Poincare coordinates that you're familiar with, how you express ADS spacing. Okay, and there's a transformation between these two coordinates when expressed in null coordinates. Okay. More setup. So the kind of black hole I want to study is not just an eternal black hole in ADS, but one that is extended into a sort of a flat space region. So here, if we just focus on the picture for a moment, here we have a black hole in ADS2. So the metric here in the center is ADS2, while the metric here in the outside parts, in these wings that I've attached to the ADS2 spacetime, is going to be flat space. So it's given by this metric, dy plus y minus. What we did essentially in joining this flat space region to the bulk ADS2 spacetime is to identify the bath time with the external black hole time near the boundary. Okay, so remember there was a time coordinate u that went up along this boundary, like so. We identified that time with the time in these external bath regions. Okay. And a comment about boundary conditions for this model. The first is that we want to impose Dirichlet boundary conditions on the metric and the dilaton on the boundary of ADS2, which is I'm calling boundary M2. So that's going to be Dirichlet conditions along these curves. And we are going to impose Neumann or transparent boundary conditions on the matter fields. So in this setup, gravity is confined to the ADS2 region, while matter that coupled to gravity here is allowed to escape the ADS2 region to the flat space region where gravity is fixed. And similarly, gravity in the flat space region, matter in the flat space region is allowed to fall into the ADS2 region. Okay, so these are the boundary conditions that we are going to work with. I should say that if there are questions, please interrupt me. I'll wait here for 5 seconds to see if there are any questions up to this point.
Yeah, there is some question in the Zoom chat from Arif Mokt. Where is the black hole singularity in the Penrose diagram?
Good, good. So in this model in JT gravity, it's not clear that there is actually a singularity. It depends on how you view the model. So JT gravity could be thought of as a dimensional reduction from a higher dimensional theory. And then in certain instances, you can imagine the singularity, it looks like a Reisner-Nordstrom singularity. Singularities they start at this point and they go upwards like this, and down here, and down here. Okay, so that's where the singularity would be if you were to imagine this model as coming from some dimensional reduction of some higher dimensional theory. But when we just study this model by itself, it's not actually clear that there is a singularity.
Okay, I don't see any more questions.
I have a question.
Yes.
So, but if you just restrict yourself to this model, how does the Penrose diagram complete? I mean, what happens to this Penrose diagram if you remove the singularity?
Well, okay, often,
what happens to the geodesics which cross the horizon?
Good. So if there is no singularity, then in what sense do I have a horizon? You can sort of ask that question. Mm-hmm. In this theory, it'll become clear in the next talk, actually. I think Douglas goes into this in more detail. But the equations of motion of JT gravity, they tell you where the boundary theory lives. The dynamical information or the gravitational dynamical information in this theory is precisely the location of where this boundary lives. And these are sort of the physical asymptotic boundaries of ADS, where you would sort of that's where your dual theory would live. And when in these solutions, these eternal black hole solutions, you find that there are two boundaries, one that lies here and one that lies there. And the horizon is just the thing that sort of prohibits signaling from this boundary to that boundary. That's the meaning of the horizon here.
But I guess my question is that this manifold is not geodesic. I mean, you would try to complete, like you will try to find some kind of Kruskal extension, right?
Oh,
Your
yeah,
geodesic will end. You would extend the geodesics. You'll be forced to go inside, right? If you throw in a particle.
Of course.
At y equal to plus infinity. So where does the geodesic end? Either it ends on a singularity or it will.
This eternal black hole solution can be extended in the usual way that Reisner-Nordstrom is extended.
Okay. And then it will have a singularity at r equal to 0. Yeah, at this, which you have removed.
The singularity won't be here.
No.
The singularity will be something like this.
Yeah, like a time-like singularity, yes.
A time-like singularity.
Yes, okay.
Yeah.
Well, there was one question also from YouTube. Does this mean that the matter does not backreact in the flat region?
Correct. In the flat region, there is no gravity. Okay, so you can think of it as, well, I mean, the action for the model, there is just no gravity action here. You can think of it as we've taken G Newton to be 0 in the flat space region. Okay, so I think I should move on for now and take questions later. Okay, here's a statement I want to make. So, what do we mean by this transparent boundary conditions on the matter fields? You can think of it in this way, which I'll explain below. The definition of these transparent boundary conditions is that the stress energy tensor is continuous in the Bath conformal frame. This will be explained below. So let's discuss the CFT quantum state. Okay, there's going to be 2 parts. So part 1, let's think about the stress tensor. So this is a conformal field theory. So we have holomorphic factorization. The stress tensor, you have a right moving and left moving stress tensors, which depend on, say, y plus and y minus individually. And the stress tensor can be determined completely using the conformal or the Weil anomaly. This anomaly is this statement that comes from CFT, that under a Weil rescaling going from a metric G to some metric eta, the stress tensors are related, these left-moving or right-moving stress tensors are related by this term here. This is the statement that the stress tensor in 2D conformal field theory is a quasi-primary. It transforms as a primary only under global transformations, global conformal transformations, but more generally it can it picks up this term. So here I was talking in this first line here. This was a transformation removing the conformal factor. But you can also sorry, it's a Weil rescaling. You can also think of it as a if you have the case, or if the transformation is a conformal rescaling, where you do a coordinate transformation from y to w, and then you remove the resulting conformal factor, then you find that the transformation looks something like this, where this term here is the Schwarzian derivative. Okay? One of the exercises that you'll have to do for the tutorial, if you want to do it, is to show that this first sentence implies a second one. Okay. Okay, so now let's go back to this transparent boundary condition business. So, so if we focus on the right exterior region plus Bath of the black hole spacetime, we have the following metrics. So we have this metric here in the black hole region, and we have the flat space metric here in this region. This 1/epsilon squared is inserted so that the metric is continuous as you go through. Imagine we do a conformal rescaling, or sorry, a Weil rescaling of removing this Weil factor from the ADS2 metric, so that we have a flat metric everywhere. So now we've put the entire system into the Bath conformal frame. That's what I mean. What I meant by that previous statement. Now we know that the bulk stress tensor is 0 in the ADS2 spacetime. Remember, it was a vacuum solution, and you can show using the equations above that this would imply that the stress tensor in the flat conformal frame is just a constant as written here. Since the stress tensor is continuous along, well, everywhere here, in this frame, there are no boundaries. This stress tensor here extends to the Bath region, and therefore this is nothing but the Bath stress tensor, and it's just a constant, and depends on the temperature or the inverse temperature beta. And so this tells you here that in this black hole spacetime we have the black hole is in thermal equilibrium with some with a bath of some temperature beta or 1/beta. Okay. Next, let me talk about another aspect of the quantum state. So far we just talked about the stress tensor. Now let's talk about sort of in more detail, what does the quantum state look like? And I've titled this section as the semi-classical Hartle-Hawking state. So we want to determine the quantum state of the matter. Again, we can use the conformal anomaly or we can do a coordinate transformation to find a coordinate W, which covers the entire sort of causal diamond, or it contains the two Bath regions and the ADS2 region in this diamond like this, such that the stress tensor in this W conformal frame is equal to 0. Okay? I claim that this coordinate transformation would do that for you. Okay? So we started with something like this. The stress tensor was 0 here and non-zero outside. We do this coordinate transformation and we find that the stress tensor is 0 everywhere in this causal diamond. This trick allows us, or it tells us that in this W conformal frame, the state is nothing but the vacuum, like the actual vacuum with respect to the Hamiltonian in the W frame, or the time translation operator in the W frame. So we know that the state is the vacuum. And so this is just usual vacuum in Minkowski space. We know that in Minkowski space, we can decompose the vacuum in terms of eigenstates of the boost operator, or this is called sort of Rindler decomposition, which is nothing but the thermal field double state in terms of eigenstates of the boost operator, the partial U. And so what this first line here does is that it expresses you are able to express the vacuum state in these coordinates in terms of eigenstates of the time operator in these coordinates. Okay? And so the statement, unsurprisingly, is that you just have the usual entangled state across both horizons. If you assume that your CFT is a free theory, then this state here can be written as such. It's going to be an entangled state of mode occupation numbers. And so the picture you have is you have two horizons, and you have a bunch of entangled particles across these horizons. In this model, this is the origin of Hawking radiation. Okay? So remember in the previous section, we saw that the black hole is in thermal equilibrium with a bath. Now we have a more refined understanding of that, which is you have a black hole that's emitting Hawking radiation, but is also kept at balance by radiation coming in from infinity from the Bath region. Okay. Any questions up to this point?
There's a couple of questions in the chat. So yeah, there's a question from Arif Mort. It was a few minutes ago. I guess bus is not at the boundary, but connected to the asymptotic bulk. Question.
Yeah. So the bath, you can think of it as, so if you let's ignore the ADS2 region here and just focus on the bath region. So the bath is literally just a half space CFT, okay? and then you've taken that half space CFT and you've joined its endpoint to the boundary of ADS2. That's how you should think about it.
And there's another question also from the chat from Erez Urbach. Where is the epsilon dependence in the coordinate transformation?
Yeah, it doesn't depend on it. The reason. Okay, here's why. So if you we go up to here. This let's look at this right side. So we have a flat space metric with just a constant outside. Notice here in this formula, the difference between the stress tensors. You have to take a derivative of the conformal factor. If the conformal factor is a constant, then that doesn't do anything. So that's why there's no epsilon dependence.
I don't see other questions in the chat, and I don't see raised hands.
Okay, let's move on. Okay, so this quantum state, you can think of it. Well, if you think of the vacuum, the W coordinates, you can think of it as being prepared by a Euclidean path integral on the lower half plane. So you have something like this. So my lower half plane looks like a disk because of conformally compactified. So there's the way you prepare the state is that you just implement the Euclidean path integral in this region. It prepares some state at t equals 0, which you can evolve in Lorentzian time. Very good. The physical state with the ADS2 metric in the bulk and flat space in the bath is related to this state via this Weil transformation, as we've been stressing before. And so you can think of it as being prepared by the following path integral. So I've called it 0 tilde. It's a path integral where in this region here, you have CFT on flat space, while in this disk here, half disk here, you have the CFT path integral on ADS2. Okay? So this path integral transitions from a flat space region to an ADS2 region, and it prepares for you some state at t equals 0, which you evolve forwards. Okay? This prescription is called, sometimes referred to as the semi-classical Hartle-Hawking state, and which is what I just said. It's the matter path integral evaluated on a fixed, non-fluctuating background. Okay, and so to summarize everything up to this point, what we did was we constructed an eternal black hole inside of ADS that is in thermal equilibrium with incoming radiation from an external bath. Let me wait for, so let me pause for 5 seconds again for people to ask questions.
Yeah, there is one new question. I think the person also raised a hand, so I guess he can unmute.
Yeah, my question is about your previous model of black hole radiation. How can radiation come back to from infinity? I mean, I think you're putting some transparent boundary conditions, so radiation should leak out from the black hole region. So how can it come back?
Good question. So the radiation doesn't actually come back. The quantum state that I've prepared here is that you have a lot of radiation coming in from infinity. That's how I've sort of initialized the state. So you have a lot of radiation coming in for all time, and the black hole radiation, and the black hole emits radiation outside. No radiation gets reflected. So whatever comes in just falls into the black hole, and whatever goes out just goes out to infinity. It's just that I have this is a sort of a fine-tuned state in that this process happens for all time. Did that answer the question?
Oh, I think the person wrote thanks in the chat. But okay, there is another question from Advait Gaikwad. Is the state factorized between ADS2 region and bus region, or on any one particular side, left/right?
The state right now, it looks just like the state, like the vacuum state in flat space. So if you want to call that a state that well, the state doesn't factorize. There's entanglement between various regions, but if you mean that the Hilbert space factorizes, if that's your question, then it factorizes in the same sense that it does in continuum quantum field theory, which I guess means that it doesn't actually factorize. Yeah, so I would say it's in that same sense. So you should think of the field theory here as just like a usual field theory on the real line. Okay. Moving on. So now I'm going to switch gears. I'm going to talk about entanglement entropy. It's kind of related to the last question. How am I doing for time?
Well, okay. So you have well, sorry, 35 more minutes, but it should include some kind of question time at the end.
Very good, very good. Okay. So now let's talk about von Neumann entropy. Okay. So the von Neumann entropy given by the following formula. If I give you a density matrix, it's just given by negative trace rho log rho. This von Neumann entropy is a measure of the entanglement of a subsystem in a bipartite system, which is prepared in a pure state. For example, if you have two qubits in the following entangled state, if you just apply this formula for the density matrix of A or A bar, you'll get log 2. Okay. So that's easy enough. But now we want to talk about computing entanglement entropy of a subsystem in a conformal field theory. And here I mean one that is in flat space in the vacuum. So it's complicated in general. And the usual trick to compute the entropy is to use what is called the replica trick. So you express the von Neumann entropy as negative partial n of trace rho to the n. Then you take, so you compute trace rho to the n, take its derivative, and then take n goes to 1. So the first step is to compute this trace rho to the n, which is often called the Renyi entropy. So how do we compute the Renyi entropy? So first, let's talk about constructing the density matrix of some interval A in the vacuum. So suppose we start with the vacuum state, here written as a density matrix. The way this state is prepared is you have the path integral from -infinity up to some point that prepares the state for you. And you can also have the copy where you go from, I guess, whatever, +infinity down to 0, and that prepares for you the brawl. Okay. So this picture here represents this density matrix. If we want, so this density matrix, which is just a pure density matrix. But suppose we want to compute the density matrix of some region A, so that's rho A. What we need to do is we need to trace over the complement of A. So that's trace over A bar of the state 0, 0. What this trace A bar means from the path integral perspective is that you simply sew these two A bar regions together and those two A bar regions together. And so the path integral is continuous in this region, okay? And so now the path integral with some boundary conditions I and j for these regions is what prepares for you the matrix elements of rho A ij. Okay, so that's how you construct the density matrix. Are there any questions about this slide? Let me wait for 5 seconds.
I don't think there is.
Okay, very good, very good.
I mean, there was some question in the chat, but it was answered by Edgar Shagulian.
Okay, great. Okay, so that's the density matrix. But now we want to compute the Renyi entropy, trace rho to the n. So the way you would do this is, well, so if you have rho ij, all you need to do is multiply it n times and then take the trace. So from the perspective here, trace roll to the n will be nothing but the path integral on n copies of the CFT glued consecutively along the interval. That's how the matrix product is implemented by the path integral. So here, what you often say is that the Renyi entropy is given by the path integral on the replicated manifold. Okay, that's what this is called. Sometimes it's convenient to collapse this replicated manifold into what's called the branched cover, where you express everything in terms of a single, you express it in terms of a multi-sheeted plane. So, here in order to be able to go between the many copies, you put a branch cut and 2 branch points on this plane. So if you go into this branch cut, you go from one sheet to the next sheet. And I guess the angle around any one of these branch points is 2 pi n. Okay, so to compute the Renyi entropy, you have to compute or evaluate the path integral on this manifold. Now, in 2D CFT, there's a simplification that happens, which is, so first of all, you can think of this calculation as starting with what is called the orbifold theory, which is just n copies of the CFT modded out by Zn, which is this replica symmetry, the symmetry that cycles you along the different replicas. And you simply evaluate a correlation function of what is called twist fields, which you can think of as being responsible for these branch points in the branch cut. So the twist fields, they live at where these branch points are. So let's consider a simple example of computing the entropy of a single interval. Let me see, how far can I go? Okay. So for a single interval, there are only 2 branch points, and therefore it's a 2-point function of twist fields. The simplification in 2D CFT is that these twist fields transform or behave as primary operators with a conformal dimension given by this C over 12 times n minus 1 over n. And because it's a primary field, the 2-point function is fixed. It's universal. It's just given by the distance between them raised to this power, which is just L raised to this power. So L is the distance or the length of the interval A. If you just take this formula now and just apply the rule for computing the entropy, you will find an expression which looks like this. C here, I guess maybe I said it before, maybe I didn't. C is the central charge of the conformal field theory. You can think of it as sort of, it's like the number of different fields in your theory. So if you apply the formula above, you'll get C over 3 log L, okay? But it's actually, so it's not, even though I didn't discuss it above, you should also put in by hand, at least at this point, something that gives you an argument of the logarithm, which is has dimension 0. And with the thing you have to put in is ultimately going to be the cutoffs. You need to well, these are 2 regulators that come from renormalizing the twist fields. Okay, I'll give you a more physical interpretation of them in a second. So and there's 1 regulator per twist field. Okay, physically, what this regulator does is that you can think of it as removing the UV divergent amount of entanglement near the ends of the interval. So if you have, so suppose we were trying to compute the entropy of an interval A, these cutoffs epsilon 1 and epsilon 2 are some cutoffs near the endpoints, which remove all this infinite amount of entanglement across these interfaces. Okay, that's how you should think of this epsilon. And so that's the case for the single interval. But now suppose you want to compute the entropy of two intervals, then it's going to be a 4-point function of twist fields, right? And the problem with a 4-point function is that it's not universal. It depends on the details of your theory, but it can sometimes be evaluated in a so-called OPE limit, where the endpoints of the two intervals approach one another. So in this case, for example, if you take x1 goes to x2 or x3 goes to x4, if they're close by, then you'll find that the 4-point function factorizes into the product of two 2-point functions. And then you can show by formulas above that the entropy is just simply going to be the sum of the two entropies. Okay. I think that's all I wanted to talk about for the first lecture. So now let me open it up for questions.
Well, then we can thank Ahmed for the lecture. We can you don't tell please unmute yourself. And okay, so there is one question in the chat from John Le Madrid. If you have a scalar as our conformal field theory in the black hole, it must have conformal weight equal to 1, and we need to input transparent boundary conditions. Then correlators of the scalar will decay exponentially in the time inside the black hole, as we expect, question mark. Does Newman boundary condition specify the mode of decomposition of the scalar field? Thanks. That's the question.
Can I actually read the?
I think it was sent privately to me.
Oh, I see.
But,
can you read it again?
if we have a scalar as our conformal field theory in the black hole, must have conformal weight equal to 1. And we need to input transparent boundary conditions, then correlators of the scalar will decay exponentially in the time inside the black hole, as we expect, question mark. Does Newman boundary condition specify the mode decomposition of the scalar field?
I think the answer is yes, although maybe there's a subtlety that I'm not.
I don't know if the person wants to unmute and
well, hello. No, so because hello, well, I am Joan, so I am trying to study these topics, and I was wondering, in general, when we have to calculate correlators, for example, in Poincaré, and then, for example, or we have to calculate correlators in these areas to black hole. In general, what we know is one of the main features is that the 2-point function, when the points are separated time-like and are very long separated, they fall off.
Yes.
In general, I don't know if that's completely related to the boundary conditions we imposed when we solve, for example, the Klein-Gordon equation. And I am not sure if that will also hold when we impose these Neumann boundary conditions. I am wondering how correlators behave inside this type of black hole with these boundary conditions.
Yeah, I think that exponential fall off is independent of the boundary conditions.
Okay.
That's my belief.
Okay, thank you.
Okay, we have a raised hand from Pedro Jorge Martinez. Yeah, you can unmute yourself.
Can you hear me?
Yes.
Great. Some slides ago, you have an Euclidean path integral which had to do both the flat space-time Euclidean path integral coupled to the ADS. That one, yes. Do you expect that path integral to be, I wouldn't say modifiable, but do you have any hope of doing like some sort of back reaction, like a modification of that path integral, because you have this region where the two theories are glued together? How would you do some sort of back reaction to that path integral? Or you do you have any hope of doing some sort of deformation to that?
I think the quick answer is yes. We will discuss back reaction in the 4th lecture.
Okay, and something, would you keep the gluing conditions untouched? Or, I mean, do you do back reaction in each space separately, or do you do something that has to do with both space-time at the same time?
Both space-times at the same time. So the back reaction here ultimately is going to be how the ADS2 region is glued to the flat space region. And there's going to be, there's an interesting back reaction between that gluing procedure and the stress tensor in the flat space region. I'll discuss this at length in the last lecture.
Oh, okay. So it's something that, oh, sorry, one last question. It has to do with the low dimensionality of the problem, right? Because if I try naively to do this in higher dimensions, it will be a very complex problem.
Yeah, it's more complicated in higher dimensions, but I don't think there's conceptual difficulty.
Okay. Okay. Thank you very much.
Yeah.
There is also right hand from Tijli Palkar. Yeah, you can go ahead.
So sorry, Ahmed, the one question I have is that the center, this CFT that you're talking about, and the C that you're talking about, is it the CFT for the flat space plus ADS? I mean, what CFT are you talking about at the moment?
I forgot to emphasize that the CFT is the same in the flat space region as in the ADS2 region. They just differ. They just differ in the background metric they live on.
So it's not like you're doubling the CFT. I mean, you're adding a. I mean, I would have imagined that the ADS has a boundary CFT. But
Yes.
that same CFT cannot describe also the external region. How should I think about this?
Let's take this step by step. So suppose I give you 2 flat space boundary CFTs. Okay.
Yes.
Let's suppose that they're governed by the same Lagrangian. So they're the same. They have 2 copies of the same boundary CFT. You can imagine quenching these 2 theories, where the quench is the process of removing the boundaries between them. So people have talked about this kind of procedure. So even though I'm not discussing a time-dependent scenario, but there are similar models where you start with a BCFT in ADS2 and a BCFT in the flat space region, and then you join the 2 boundaries so that now instead of a 2 half space CFTs, you have a single CFT on the real line.
Okay.
Well, there was a few questions in the chat, but I think some of them may be already answered by Edgar. Yeah, you can take a look yourself if you want.
I trust Edgar.
Let's see. Yeah, well, there are also a few questions which wrote. Okay, let me see. Well, there was some questions which wrote to me privately. So, for example, the question from Jivan Chandra Namburi, can we think of the entanglement entropy as the sum over entanglement entropies due to the left and right movers? What happens if there is some sort of a mirror in the space-time which converts left movers to right movers?
So in yeah, so in this case, in the CFT, the entanglement entropy is really the sum of the entanglement entropies of the left movers and separately for the right movers. There's a factorization that happens. But if you have a mirror, then that factorization is not there anymore. But still, the formula is very similar. It's not changed much. So essentially, all that changes is that the C/3 becomes a C/6. Becomes a C/6 if you have a mirror. But in our case, we don't have that mirror, and Yeah, so the only statement is that when you have a mirror, it's not complicated by too much.
Thanks. Okay, there's another question from a private chat from Advait Gaikwad. How do you couple a general CFT2 on a half line to SYK model or a CFT1? I guess index means dimension, in order to get the dual picture described here.
Good. So.
Okay, it was asked also publicly in the chat. Yes.
Okay, so let me see. Let me go back. Bigger picture, it's better. So yeah, maybe this is worth explaining at length. So another picture you can. So if you ignore the two flat space regions, this ADS2 region, this ADS2 spacetime, or the JT gravity, you can think of hand-wavingly that it might be dual to two boundary theories living on the two boundaries. So these are just 0+1 quantum mechanical systems. And this process of joining in this flat space region is getting something like, well, as I said before, a half-line field theory, which you couple to the boundary quantum mechanical systems. Now, let's suppose that the boundaries are SYK. So I have two SYK Hamiltonians here and here. You can imagine introducing a spin chain. You have spin chain here and a half spin chain there, and you introduce some simple interaction between the SYK Majorana fermions to one end of the spin chain. And the interaction, I think, doesn't have to be complicated. It can just literally be like a bilinear between a fermion. Maybe bilinear doesn't work because of fermion statistics and so on. No, I mean fermion bilinear is bosonic, but to preserve some symmetries of SYK, maybe it's better to put two fermions of SYK coupled to two fermions at the end of the spin chain or something. But that's detail. But yeah, so you can think of this as a toy model of a model of a more realistic model like that, where you have SYK here coupled to the end of a spin chain, and then the remainder of the spin chain.
This is Advait. Sorry, I would like to just clarify on this question. I was really asking for the detail. So in general, if I couple a single trace operator with a source to a CFT, the dual picture, you get scalar fields in the bulk. Now I don't want to couple. I want to couple a large CFT or some high dimensional CFT. What is the structure of the entanglement which says that the dual picture in the bulk also has the same CFT in the bulk?
Oh no, I don't have an answer to that question. That's yeah. So here we're making this assumption that the CFT here is the same as the CFT there, and you wanted something like that in higher dimensions, maybe. Is that roughly like that's the thing that you're focusing on? That the same CFT here lives here?
Yeah. What kind of interaction in the CFT D coupled to CFT D+1? What kind of interaction term will dictate that in the dual bulk picture, it's the same CFT D+1 is also on the bulk?
So if we think of just usual ADS CFT, so I have a stack of D branes in whatever 10 dimensions or whatever. This stack of D branes in the decoupling limit becomes ADS. But the theory living in the ADS throat is the same as the theory that lived outside of the ADS throat. They're both string theory, but one is in ADS space and one is in flat space. So the fact that the matter theory in the ADS region is the same as the matter theory in the bath region is actually quite realistic from the example that I just gave you. But they're not going to be CFDs. Maybe, I don't know if that was essential for you.
Well, I mean, yeah, maybe not really.
Okay, but the point that the same matter theory lives in the ADS region and in the flat space region is
Yeah,
something which is natural.
I see. Okay, thank you.
Mhm.
So there is a raised hand from Ricardo Espindola. Yeah, you can unmute yourself and ask.
Yeah, Ahmed, in your example, the one that you just gave, how can you neglect gravity at infinity from this CFT?
Well, in the example,
And maybe more interestingly, can you imagine some kind of UV completion or string theory description of this type of CFT coupled to ADS2 with matter?
I cannot. Well, I'm not that sophisticated in string theory, but yeah. So for that question of getting CFT coupled to ADS2, I think there's previous work of Strominger and Giddings, where they talk about the CGHS model and how you might get something like a CFT coupled to CGHS, which you might extend to also cover JT gravity. But maybe there are other experts that can shed more light on that. Let me see. Yeah, but for your first question, how can we approximate that the flat space region in the string theory example is like having non-dynamical gravity? You can imagine only considering questions where the back reaction is important in the ADS region. And if, I mean, this is not that precise. Or maybe I should just not say anything about that.
Okay, thank you.
Yeah, there was quite a few questions in the chat, but I think they were more, yeah, they were all at least at some level addressed by Edgar. But I mean, I don't know if Ahmed, you want to take a look. But yeah, I suggest yeah, maybe like if you feel to be missed out, you just raise a hand and then we will unmute you and you can ask verbally.
I guess people can also just ask questions on Slack.
Yeah. If you yeah, you can ask it. Yeah, everybody is very welcome to ask questions and answer questions on Slack at any time. Okay, there is a raised hand from Arif Mort. Yeah, please, you can go ahead.
Hey, can I think of this joining region where the bath and the bulk are joined as just think of as a brain inserted, where on one side of brain you have flat space and the other side of brain you have this CFT living on the bulk ADS2. But then is there any because the anomaly on the two sides will be different. CFT on the bath side is on the flat space conformal anomaly is 0, while on the bulk side on the ADS2 side there's some non-zero conformal anomaly. So is there some matching condition on this boundary?
Yeah, maybe you can think of this as Yeah, so the way that we've defined the transparent boundary conditions is by going to this conformal frame where the stress tensor is the same everywhere. So there's no brain partitioning the two regions, and stress tensor is just continuous. But you can imagine working in this other frame. Let me go down. This frame here, where I think you might be able to express. So now here the stress tensor here is different than the stress tensor there, but now you can think of there being a brain here, and whether this can be expressed as some junction condition between the two regions. Maybe there's a way of expressing it like that. I haven't thought too much about it.
All right. Okay, thank you.
Well, there's one new question in the chat. Well, in the public chat. Well, I guess I can read it if you want. Do observables? Yeah, the question from John. Do observables in the internal ADS2 black hole really feel, in quotation mark, there is a bus coupled to in the boundary? I mean, dynamics will be altered somehow in the black hole. Or is the boundary bus just used to have a region with Hawking radiation and be able to study the page curve?
I think both. I think correlation functions in the Bath region are sensitive. Sorry, correlation functions in the ADS2 region are sensitive to the fact that there's a path. I mean, the correlation function, I mean, for the same reason why a correlation function in a BCFT is different than a correlation function in a regular CFT. The correlation functions are sensitive to whether there's a boundary or not, because of boundary conditions and so on and so forth. But ultimately, as you said, this model is constructed to ultimately to answer questions about page curve and so on.
Yeah, so I don't see any more new questions. So again, yes, so yeah, you can always feel free to ask a question on a Slack, and you also will have opportunity to ask questions during tutorials. But yeah, for now, let's conclude, and let's thank Ahmed again.
Thanks.
We will resume roughly in 1 hour, 45 minutes with a lecture from Douglas Stanford about more on quantum black holes. Have a nice break.
Yeah, sure.
Hi, Pavel.
Hi,
How are you?
I'm good. How are you?
Good, good, yes. So I'm gonna be doing just regular slides.
So, well, let me stop my sharing. And yes, this is just a message how these questions will be handled.
Okay, well, maybe I should read it. Let me see.
Okay, yeah. I mean, if you want to, yeah, if you want to manage it differently, let me know.
Okay. Write your question. Okay.
Yeah, but yeah, if people write me in the chat, I will just read them to you at some point.
Hi, Douglas. Good morning.
Hi, Atish. Hi. Good
Hi,
morning.
how are you?
Or good evening, I guess. I'm fine. Yeah.
Yes, good evening for us.
Yeah, this method for questions is fine, but I also don't mind if people just interrupt me to ask questions. So
Okay.
it depends, I guess, if it's like urgent or not.
Yeah, it more or less worked like that in the first two lectures, and I think it worked well. People more or less asked questions when they wanted, no? Pavel?
Okay.
No, I don't. No, I mean, I transferred the question.
No, you transferred the questions, that's good, but more or less, it's not that they waited till the end of the, like after 15 minutes, they asked the questions, right? Something like that, 10 minutes. So it was fairly continuous, not
Okay.
in the end. So.
Yeah, that sounds good. I mean, that to me, it's one of the main benefits of doing this live as opposed to just watching something on YouTube or whatever later, is you can ask questions in real time. So we should really try to accommodate that.
Yeah. So great. You have a nice carpet behind you, is it?
Yeah, this is a, it's called a tapa cloth.
What is it called?
It's called a tapa cloth. I'm actually, so I'm kind of fleeing the wildfires in California, and I'm in Washington State right now, and I'm in my mother's garage, and to make it look professional, I put this.
So it's a real background, it's a virtual background.
It's real. Look.
Okay. Okay, good.
Yeah.
Great. So I'm looking forward to your talk now. It's in 1 minute, huh?
Okay, yeah.
So I can probably stop sharing.
Okay, sounds good. Yeah, I'll share my screen then.
We had fairly good. We had altogether maybe 125, no? Pavel, yeah.
Well, it's fluctuating, I think.
Yeah, it fluctuates, but okay, the maximum was 125.
How is this?
Yeah, we can see it well, and we can see some sort of, no, it's gone.
Glowing object? Okay, the only problem is that the way I'm sharing this screen right now, I can't see anything. Like I can't see the Zoom interface at all, so I can't.
Yes, that's why I will read you from the chat.
Okay.
So by the way, Douglas, one thing I tried to avoid this problem, which you might want to try tomorrow, not today because you don't have the time, is to log in from 2 separate devices. And with the same account. And then you can use one thing for Zoom so that you can see everybody, and the second one for projecting your slides.
Okay.
And that second one, you have to remember to, however, switch off sound completely. If you do that, it actually works very well. This is what I did. I shared from the iPad. You might want to try that tomorrow.
Okay, let me.
It can help you to with the technical thing if you need.
Let me try one other thing. Just, I think this will work as a alternative. How's that?
Well, it's about the same.
Okay. Yeah, now I can see the people, so this is probably better.
That's good then. If you can see the people, that's good, because this is good enough.
Okay.
Yeah, when you when you find some appropriate times to pause in your lecture, you can let me know, and then I can transfer. So I'm not so that I don't interrupt you. I can transfer you the questions.
Oh no, just interrupt. I don't mind. Interrupt like whenever, as soon as you get the question. Just yeah.
Okay.
Yeah, and like I said, so people, yes, to participants that I mean, they can write the question in the chat, but they can also raise a hand, and then they will be unmuted. Yeah, don't be afraid to raise a hand and ask a question. So if you're ready, I think we can start probably. It's time.
Okay.
Well, I can introduce
Okay.
So yeah, so we are happy to have Douglas Stanford, and he will give us a lecture course on quantum black holes.
Okay, thank you. It's a pleasure to be lecturing at this school. I'm really glad that it's happening. And my lectures are going to be sort of supporting the lectures of Ahmed Almiri. So I'll cover some of the same topics, sometimes from a different point of view and in a different context. And hopefully that will help reinforce some of the things that he's teaching you guys. And as we mentioned at the beginning, I don't mind if people ask questions during the talk. I think that's really important as a way to make sure that what I'm saying makes sense. So please don't be shy to raise your hand, write in the chat, or to be honest, even just to shout out and interrupt yourself. So, okay, so let's get started. So the basic claim that we're going to be exploring today and the next few days is this amazing idea that from a distance, a black hole behaves like an ordinary quantum system with many degrees of freedom and strong interactions. This is by now it's sort of an old idea in theoretical physics, and it's been driving a lot of the most exciting progress in the last several decades. So this picture here is supposed to represent a black hole that you're viewing from a distance, somehow a black hole that you have in some kind of box, and then some kind of measuring device. And the content of the claim is basically that if you didn't know what was inside the box and you were doing experiments on it using this measuring device, you would conclude that what you have inside there is some kind of ordinary quantum system with many degrees of freedom and with strong interactions. So we would like to explore this. In particular, we'd like to check it, to see what it means, and to try to do some of these experiments from a distance on the black hole. So what are we supposed to compute to check this claim and to understand it better? So today we're going to talk about two different things that you can compute. The first one is the thermal partition function, z of beta. So beta here is the inverse temperature, 1 over T. And z of beta is just the standard thermal partition function, trace of e to the minus beta h. So we're supposed to compute something like that for the black hole and see that it resembles what you would have found for an ordinary quantum system with many degrees of freedom and strong interactions. Okay. The second thing we'll discuss is a little bit more detailed. It's a real-time correlation function, g of t. So it's a 2-point function in the thermal state. And this is one of my favorite quantities. It tells you so much about the physics of the system. In particular, it can tell you about how the system thermalizes. So what happens when you introduce a small perturbation in the system. Okay, so those are the two things that we're going to discuss today. So to be consistent with Ahmed's lectures, we're going to work with this two-dimensional gravity theory that he introduced earlier today, Jacobi tidal point gravity. So I'll remind you a little bit about the theory. I think you've seen these formulas already, but I here is the Euclidean action. And for JT gravity, the Euclidean action looks like this. it has this first term here, which is the Einstein-Hilbert term in 2 dimensions. That term is topological invariant, proportional to the Euler characteristic. So this term is sort of not that interesting in 2 dimensions. So we add to it a second, more interesting term that involves an extra scalar field phi, the dilaton. So we have an action that has the dilaton phi multiplying the scalar curvature plus 2. And the choice of 2 here is a matter of convention, just determines the units we're working with. Okay, so that's JT gravity. It's a 2-dimensional gravity theory, and the dynamical fields are the metric, g mu nu, and this extra field we introduced, phi, the dilaton. And as Ahmed showed you, this theory has ADS2 black hole solutions. I think he discussed this black hole mainly in Lorentzian signature, where it has a horizon, an interior, an exterior, and was kind of obviously a black hole. What we're going to do is we're going to mainly discuss that same black hole in Euclidean signature in order to compute these things that I mentioned before. So in particular, we're going to compute the thermal partition function z of beta and correlation functions g of t. Okay. So I wrote this action out here, but if we're a little bit more careful, then we should introduce some boundary terms. We're going to be studying this theory on a space with a boundary, and we need to add some boundary terms to this bulk action. And if you're careful and write out the action, including the boundary terms, what you find is the following expression. So let me just explain what we have here. The first term is the completion of this first term up here by adding a boundary term, where chi means the Euler characteristic. So S naught is some parameter that we should imagine is large, and it multiplies the Euler characteristic. That just weights different topologies differently. So this is a relatively boring term in the action. And then in brackets, we have the completion of the term that we started writing up here in the first line. We have that same bulk term, but then we have to add to it this term involving the extrinsic curvature k on the boundary. This is basically just the standard Gibbons-Hawking-York boundary term associated to this bulk gravity term. Okay, so that's all there is to the action of JT gravity, and we're going to come back to it in a moment once we figure out what we are supposed to compute. Okay. So our first goal is to compute the partition function, z of beta. So how do we compute that? Let's think first about a normal quantum mechanical system. So if we just have some ordinary quantum mechanical system, to compute z of beta, which is trace of e to the minus beta h, what you can do is you can think about this in the path integral formalism. What you do is you take the path integral of the quantum mechanical theory on a circle of circumference beta. So we think about the thermal system as being periodic in imaginary time with periodicity beta. So this time, this circle that we're talking about here is the circle of imaginary time, has circumference beta. And to compute the thermal partition function in quantum mechanics, you just study the path integral on a circle. Okay. That's if we had some ordinary quantum mechanical system. We don't. We have a black hole, all right, 2-dimensional theory of gravity. How are we supposed to compute z of beta for the black hole? So people figured out how to do this before the ADS-CFT correspondence, but it's kind of convenient to think about it in the spirit of the ADS-CFT correspondence. And in particular, we can use a very, very simple version, just a piece of the ADS-CFT dictionary, which says the following thing. It says that the space that the boundary theory lives on should be a boundary condition that you fill in with the bulk theory. So that's some general thing. Let's explain it in very concrete terms for the case that we're discussing here. So we want to compute z of beta. The space that the boundary theory lives on is just the space that we've been discussing so far, the circle circle that you put the quantum system on to compute its thermal partition function. So in order to compute z of beta in the boundary theory, which is an ordinary quantum mechanical system, we would just put the theory on a circle. Now, the ADS-CFT dictionary says that in order to compute that using the bulk, using the gravity theory, using our two-dimensional gravity theory, what you're supposed to do is you're supposed to view that circle as a boundary condition. And you're supposed to fill it in with two-dimensional gravity. So z of beta in the boundary would be computed on a circle. Here we view that circle as a boundary condition, and we imagine integrating over two-dimensional metrics that end on that circle. So that's how you compute z of beta for this problem. You just integrate over two-dimensional metrics that have a circle as a boundary. So more precisely, we should impose the following boundary conditions on our two-dimensional gravity theory. The circumference of this boundary circle, so we should be studying gravity on a manifold with the topology of a disk. It has a circular boundary, and we should impose that its length is beta divided by epsilon, where epsilon is a holographic renormalization parameter. We'll take it to 0 at the end. So that's the geometrical boundary condition. Because we have this extra scalar field phi, we also need a boundary condition for that. And its boundary condition, it's convenient to take it to be 1/2 divided by epsilon. We could have put another number here instead of 1/2, but I like putting 1/2 there. So these are the boundary conditions, and we're supposed to take epsilon to 0 at the end of the calculation. So you should think of this as being a two-dimensional gravity region with a very big circle as a boundary, proportional to beta divided by epsilon, where epsilon is going to 0. Okay. So in principle, what we should do is to compute z of beta, we should do the full path integral. We should integrate over two-dimensional metrics and also over the dilaton. We should integrate over all possible configurations of these fields with the condition that they satisfy the boundary conditions we just discussed. So we have this big circle of length beta over epsilon, and phi is equal to 1 divided by 2 epsilon. Okay, but for now, we're going to be a bit more modest. We're going to work in a classical approximation to this functional integral. The classical approximation means is that you just solve the classical equations of motion of the theory, and then plug them into the action and take that as an approximate answer for the integral. It's like a saddle point approximation or stationary phase approximation to this path integral. And to evaluate it, what we need to know is the action of the classical solution that satisfies the boundary conditions we've discussed. Okay. So first, we're going to describe what this solution is, and then we're going to plug it into the action to compute.
I have a question.
Yeah.
So I would have thought that the physical circumference should be beta, right, at infinity. In the limit epsilon going to 0, you're saying the circumference of the boundary is beta over epsilon?
Yes.
And not
yeah,
beta?
Right. So the physical proper length of the boundary is it's big. It's beta over epsilon as epsilon goes to 0. So this is kind of familiar from higher dimensional examples of ADS-CFT, where you take this limit where the boundary is very big and very far away. But
it's ADS back. Okay, it's not like I should not think of it as a black hole. In the Euclidean black hole geometry, the beta is fixed. So
well, that depends what kind of black hole you're talking about, I guess.
Schwarzschild black hole. I was thinking of Schwarzschild. Okay.
Well,
Schwarzschild
I guess
black hole, it's really like a cigar rather than. Okay, but
yeah.
I think it's ADS. I think you probably have it in mind ADS. Okay, I will.
Yeah, I think it's easiest to think about this translation between partition functions and gravity computations in the context of ADS, but you're right, it can be discussed in other cases.
The asymptotics is ADS.
Yeah, and this scaling with epsilon is a particular property of things that have ADS asymptotic. So yeah, that's an important thing to emphasize. So thank you, Atish.
There's also another question from raised hand from Himanshu. Yeah, you can go ahead and
So just wanted to make sure. So far, we haven't used the fact that there's a black hole in the ADS2, right? We are just
Okay, right, good. So where is the black hole? The black hole, I'm actually about to show you, but the black hole is this disk geometry. So a black hole in Euclidean signature, so for Euclidean time, is a disk geometry. So earlier today, Ahmed discussed the black hole in Lorentzian signature, where there was a horizon and it was more obviously a black hole. And here we have a geometry that's basically a piece of the hyperbolic disk. And the key feature that makes it a black hole, okay, you can ask, what is a black hole in Lorentzian signature? And well, that's basically a solution with a horizon. What is a black hole in Euclidean signature when time is imaginary? And what it is there is it's a solution where the time direction is a contractible circle. So the time direction for this geometry is the angular direction. And you can see that it's contractible in this geometry. So that's the definition of a black hole in Euclidean signature.
it is just one of the solutions of the equations of JT gravity. And when you are computing the path integral, you are also like including other saddles, which might not be a black hole, like which could just be pure.
Yeah, that's good intuition in general, especially for higher dimensional theories. But for JT gravity, the only classical solution is this black hole solution. So there's no other thing that we're supposed to include.
I see. Okay, thanks.
Okay, so let me remind you where we are. We're trying to compute this partition function by finding the classical solution and plugging it into the action. So let's first describe what this classical solution is. So the classical equations of JT gravity, I'm not going to write them for you, but they're what you get by varying the action we wrote before. These equations have a one parameter family of solutions, which can be written in this way here. So the metric is d rho squared plus sinh squared rho d theta squared. And you might recognize this as two-dimensional hyperbolic space, just the two-dimensional hyperbolic plane. And phi is equal to some parameter phi h times cosh of rho. So the one parameter family refers to this parameter here, phi h. It can take any value. Okay, so here's the hyperbolic plane. Rho equals 0 is at the center. Rho equals infinity is out here at the boundary. And there's something kind of subtle that, but very important to emphasize here, which is that there are two notions of boundary of the hyperbolic space that are going to be important for us. So first, there's the notion that, well, a mathematician would tell you about, which is the mathematical boundary of hyperbolic space at rho equals infinity, the conformal boundary of this hyperbolic disk out here. Second, there's some finite location in the hyperbolic plane, drawn here with a red curve. And that's the location where the boundary conditions we've been discussing are going to be satisfied. So the solution that we've been discussing is actually going to be just the interior of some finite region of the hyperbolic space. So it's everything inside this red circle here. So I've drawn in a lighter color the region of the hyperbolic plane outside that red circle because it's there mathematically, but it's not going to be part of the solution. Okay, so when there's ambiguity, we'll refer to this red finite boundary as the regulated boundary, but it's actually it's the physical boundary of the JT gravity region. So this is the important one, this red circle. Okay, so let's discuss now how to determine the location of the red circle and the value of phi h in order to solve the boundary conditions. So remember, we have two boundary conditions. One is that the dilaton phi evaluated at the boundary is 1/2 epsilon. And if you plug that into the formula that we had a moment ago, that tells you that phi h times cosh of rho boundary, so the value of rho at this red circle, phi h times cosh of rho boundary is 1/2 epsilon. So that's one constraint on these two parameters, phi h and rho boundary. And the second constraint comes from the condition that the circumference should be beta over epsilon. And okay, the circumference of a circle in the hyperbolic plane is 2 pi times sinh of rho boundary. And we're setting that equal to beta over epsilon. So now we have two equations for these two parameters, rho boundary and phi h, and we can solve them. Okay, let's imagine taking that solution and plugging it into the JT gravity action to compute the on-shell value of the action. So if you look at this action, there's sort of three terms. The first term is S0 times the Euler characteristic. The region we're looking at has the topology of a disk. And you might not remember this, but you can definitely look it up on Wikipedia. The Euler characteristic of a disk is 1. So the first term is minus S0 times 1. Let's look at this next term. Well, for the hyperbolic disk, the scalar curvature R is equal to minus 2. So this term here actually vanishes. So the only term that we actually have to evaluate, the first term was very simple, the second term was 0. The only term that we really have to evaluate is this third term involving the extrinsic curvature. So we need to know the metric on the boundary, the extrinsic curvature on the boundary, and the value of phi at the boundary. Okay, so that data is the following. So the square root of the metric is sinh of rho boundary. That just comes from the fact that we have a sinh there in the metric of hyperbolic space. Then the extrinsic curvature is given by this formula, g theta theta times d rho of g theta theta. And if you work that out using that g theta theta is sinh squared rho, you find the answer 1 over tanh of rho boundary. And finally, the value of phi at the boundary is actually determined by our boundary condition. It's 1 over 2 epsilon. So if we take these three quantities and plug them into this formula, we find 2 pi for the integral over the angle, sinh rho for square root of h, 1 over tanh rho b minus 1 for k minus 1, and then 1 over 2 epsilon for phi. So this is our formula for the action. And now we just simplify this expression involving sinh and tanh. We simplify that to e to the minus rho b. And then we use this equation here to substitute in for epsilon. And we find the following expression, e to the minus rho b times sinh of rho b over beta. And if we simplify that for large rho b, we find minus S0 minus pi squared over beta. Okay, so the hard work was just to compute this term pi squared over beta. It came from this extrinsic curvature term. Okay, so now we can plug it in, and we find that in a classical approximation, this partition function is equal to e to the S0 plus pi squared over beta. We should ask ourselves whether this looks like a reasonable answer for a strongly interacting quantum system with many degrees of freedom. There's more to say about this, but well, one simple thing is that the answer increases quite rapidly as the temperature increases, as we would expect for some thermal partition function. And if you look at it a little bit harder, you can compute, using thermodynamics, you can compute the energy and the entropy of the system. And for the entropy, you find this answer S0 plus 2 pi squared over beta. So that's 2 pi squared times temperature. And this behavior is consistent with the thermodynamics of some particular quantum systems, for example, the SYK model. So far, so good. The thermal partition function looks kind of like what you would expect for the partition function of a strongly interacting quantum system. Okay. So before I do the second computation, it's been about 20 minutes. So I'm going to stop here for a brief break. We'll come back and then compute G of t. So I think the best thing to do is just to take a 5-minute break. And then after that, we'll pause for questions and then we'll get going on the second half. So please just take 5 minutes to stand up and stretch or do whatever you need to do.
You want the questions to be answered after this break. This break is you want to.
Yeah, this is a real honest break. So please step away from your computer, and I'm not going to answer any questions. I'll do that in 5 minutes. So to emphasize the point, I'm actually going to get up and go and have a drink of water. So I'll see you guys in 2 minutes. Okay, it's been 5 minutes. So if anybody wants to ask questions now, then that's a good time.
There are some questions in the chat. Yeah. I mean, there's a question from Thomas Codina. Can you repeat why did you take the limit of rho going to infinity in the action?
Ah, okay, good. So I think he's referring to this step here. So we had some expression e to the minus rho and sinh rho. Why did we take rho to infinity? So in this theory, we're taking a limit. Epsilon goes to 0 of these boundary conditions. And as Atish emphasized, that's a feature of the fact that this is a theory with ADS asymptotics, anti-de Sitter space asymptotics. So we're supposed to take a limit where the boundary circle gets very big, very close to the mathematical boundary. And in the limit where epsilon goes to 0, you can see from this equation here that rho b is going to have to go to infinity. So in this expression here, we're allowed to simplify it with the assumption that rho b is very large.
Okay, there is another question in the chat from Jivan Chandra. Are we assuming that quantum corrections are suppressed somehow?
Ah, good. We'll come to quantum corrections in a little bit. But so the general story, if you have an integral like this, I think in Ahmed's lectures, he emphasized this more. He wrote the action in the way where everything is divided by g Newton. So we have a 1 over g Newton multiplying everything. In a more familiar context, you'd have a 1 over h bar multiplying everything inside the action. And then if h bar or g Newton is small, then it's a good approximation to this integral here to just evaluate it using the saddle point approximation. So the computation that we did is a good approximation in that limit. And we'll see actually that the full quantum calculation doesn't change things too much.
Okay, there are a couple of more questions in the chat. One from Sunil Sakya. Can dilaton not have more general classical solution?
Well, it could if you had a different potential for the dilaton, but in this theory, this is actually the only solution. It depends a little bit on how you parameterize the coordinates. So more precisely, there is a coordinate system where the most general solution has this form. But of course, if you choose different coordinates, it might look different, but it will be equivalent to this solution up to some change of coordinates.
And there is another question from Muhammad Al-Fiki. What does the regulated boundary depend on? And will choosing another regulated boundary, if that is possible, can make the calculation less or more complicated?
So the regulated boundary, its definition comes from our boundary condition here, that the circumference should be beta over epsilon. So the regulated boundary is some location of finite length. Sorry, actually a better way of thinking about it is the following. A better way of thinking about it is this. The regulated boundary is the location where phi has this value, 1 over 2 epsilon. So that will be at some kind of finite point in the hyperbolic plane. And it doesn't have to be a circle. So the question was asking about whether other choices of this boundary make things more complicated or more simple. In principle, we'll have to integrate over all shapes, both complicated and simple, for this regulated boundary. But we haven't got there yet. And in the classical approximation, it just has this simple form of a circle.
I don't see any more questions so far.
Okay, good.
Sorry, no, actually there is. Yeah, there's a question from Gui Silva. Could you remind us of the temperature behavior of a free quantum mechanical system to compare it to your result? When you set strongly coupled quantum mechanics, where is the coupling constant?
Good. So this behavior of the entropy, this behavior S is linear in temperature, is a sort of unusual behavior which is found in these non-Fermi liquid quantum systems. So it's, for example, well, what you're supposed to compare that, sorry, the free answer depends on what kind of free theory we're talking about. But this particular linear in T behavior of the entropy is a property that was previously known to arise in certain strongly interacting non-Fermi liquid quantum systems. So in that context, it's a signal that it's some kind of interacting quantum system that the black hole is dual to.
Yeah, now that's probably it.
Okay, so let's start with our second goal here, which is to compute the response function, correlation function g of t for some field. So for this, we're going to use a second component of the ADS-CFT dictionary, which says that correlation functions of boundary operators, so g of t is a 2-point function of some boundary operators. And the ADS-CFT dictionary says that correlation functions of boundary operators, including this 2-point function, are limits of correlation functions of bulk fields as the points approach the boundary. So let's see what that means. I'll draw a picture for you a little later. But our approach, so we want to compute this g of t in real time, where t is real, honest Lorentzian time separation of the operators. And our approach will be to compute it first in imaginary time, using this Euclidean black hole. Then we'll analytically continue the answer. So rather than computing g of t, we're going to first compute g of minus I tau. So tau is the imaginary time separation of the operators. And the ADS-CFT dictionary says that in order to compute that 2-point function, what you're supposed to do is evaluate in the bulk theory a correlator of points separated by distance tau divided by epsilon along the red circle. So naively, it would have just been tau, but because we have these ADS asymptotics, we're supposed to rescale the relationship between time on the boundary theory and time in the bulk by 1 factor of epsilon. So the separation between the points along the red circle should be tau divided by epsilon. Okay, so let's say for simplicity that we have a free massive scalar field with this action. So we have the kinetic term and we have some quadratic mass term. So if the mass m is large, then the propagator of this field is e to the minus the mass times the distance between the points. Little l is the distance between the 2 points. This is a geodesic approximation to the 2-point function of a correlation of these massive matter fields. So the recipe for the correlator is the following. Let's go back to our classical solution here. We have the interior region of this regulated hyperbolic space. So everything inside the red circle. And we're supposed to pick 2 points with separation tau over epsilon along the red circle. And then we're supposed to compute the 2-point function of the bulk fields between these 2 points. And in our large mass geodesic approximation, that 2-point function is just e to the minus the mass times the geodesic distance, times the distance through the bulk between these 2 blue points. So it's kind of interesting. In this formula, 2 notions of distance between these 2 blue dots arise. The distance measured along the red curve. So if you force the path between the 2 blue dots to be along the red curve, then that distance is tau over epsilon. And the distance through the bulk, the actual geodesic distance, is L. And in that situation, the geodesic approximation to the 2-point function of minus I tau is equal to e to the minus the mass times the length. Okay. And a subtlety that will come up when you actually try to compute this is that you need to add to this term a multiple of log epsilon so that the answer is finite as epsilon goes to 0. That can be understood as a renormalization of these operators O. Okay. So I'm not going to do this calculation for you right now. I think we'll probably go over it in the tutorial, but it involves very simple hyperbolic geometry just to compute the distance along this blue curve here. And the answer you find is the following. It's proportional to 1 over sine pi tau over beta to the power 2m. So you can see from the fact that we have an m in the exponent like we did here, that e to the minus L was basically the square of this function, the square of 1 over sine. Okay, so if we continue this expression to real time, then that sine in the denominator turns into a sinh, and we find this expression. In particular, notice that it decays exponentially in time, 1 over sinh t to some high power. So we should think about this physically. We're computing a 2-point function of some operator in this thermal state. So we act with the operator at time 0, then we act again at time t. And you can think about that 2-point function as somehow measuring the probability or the amplitude that if you create a small disturbance at time 0, that small disturbance will still be there at time t. So this function measures how likely the small perturbation that you made is to stick around, to stay visible in the thermal state. And this function decays exponentially in time. So what that says is that the perturbation is not very likely to be there anymore. So if you create it at time 0, and then you try to go and find that perturbation again at time t, you have an exponentially small amplitude for successfully finding it at a later time. So in a free theory, this thing would just oscillate in time. And in this theory here, it's exponentially decaying. So that's really a sign that this is an interesting quantum system that has interactions and that thermalizes. So I want to emphasize that even though we kind of know that if you have some complicated quantum system and you poke it with some perturbation at time 0, that perturbation is going to kind of thermalize and disappear and won't be visible at time t. We kind of know that, we can kind of feel it in our bones, but we can essentially never compute it because strongly interacting quantum systems with many degrees of freedom are just really hard to do calculations on. So we kind of know this would happen for a strongly interacting quantum system, but it would be incredibly hard to compute it. And here in this gravity theory, in JT gravity, we got the answer in such a beautiful, simple way, just from a geometry problem.
There are a couple of questions.
Yeah.
So first, yeah, there was a raised hand from Himanshu. Yeah, you can go ahead.
Sorry, what is beta here in the context of Lorentzian? You're computing a Lorentzian correlator. So
oh, good, good.
Beta.
So we're computing, yeah, so the time separation between the 2 points that we're computing the correlator at is t. So they're separated by time t, the 2 operator insertions. But we're computing it not in the vacuum, we're computing it in a thermal state. So it's the 2-point function in a thermal state where the temperature of the inverse temperature of the thermal state is beta. So that's why both beta and time t appear.
There are also a couple of questions from YouTube chat. Yeah, they were asked, I think, a few minutes ago by another blogger. So the first question, aren't we also considering 2-point functional bulk fields? And the second question, is the geodesic approximation valid for all dimensions or just d equals 2?
Ah, okay. So good questions. So we are computing the 2-point function of bulk fields, but by the ADS-CFT dictionary, the correlation functions of boundary operators are limits of correlation functions of bulk fields as the fields approach the boundary. So we've been computing a special case of a bulk 2-point function where the 2 points are actually on the boundary. So it would have made sense to have these 2 blue points anywhere in the bulk, but we're studying a special case where they're on the boundary. And the ADS-CFT dictionary says that when you study that special case, what you're computing is actually a 2-point function of boundary operators. So you can think about this as 2-point function of simple operators in the quantum system that is dual to this black hole. So the second question was about the validity of the geodesic approximation.
Yeah, in dimensions.
And okay, so good. So this formula is, the geodesic approximation is always valid for large enough mass, so in higher dimensions as well. although you have to be careful about what geodesic you're including. Here, there's really only one. In higher dimensions, there can be more than one, and it's a little bit subtle to figure out which geodesics you're supposed to include, but the approximation is always valid at large mass. Something extra special happens in 2 dimensions, which is that for the black hole solution, even for the black hole solution, this formula ends up basically being correct, even for small mass. This form of the answer ends up being correct, even for small mass. You just have to change the exponent a little bit. So in 2 dimensions, the geodesic approximation is sort of, it's more valid than you would have expected, but it's always valid at large mass.
And well, there is one new question in the Zoom chat from Said Kohli Biko. Is there any form of Birchhoff's theorem in JT gravity?
Yeah, yes, that's the statement that we have this simple solution is the most general classical solution. So the fact that this is the most general solution and that it has a U1 symmetry, which is translations in theta, that's the analog of Birchhoff's theorem in higher dimensional general relativity.
Well, there are actually more questions, but I don't know if you want to.
Yeah, no. Let's do a couple more questions and then I'll keep going.
Okay. So the next question from Jivan Chandra. So can we think of the mass of the bulk fields as a dimension of the boundary CFT operator?
Yes, that's right. And as you can see, well, that's right. For large mass, the formula is basically the dimension is equal to the mass. For smaller mass, there's a correction. It's 1/2 plus square root of a quarter plus mass squared. So there's a simple relationship between the mass and the dimension. And for large mass, it's just m equals delta.
I think that's it for now with questions.
Okay. Okay, so let's continue. We probably won't get through the full second half, but we'll get started on it and we can continue tomorrow. So on the previous slide, I was talking about how simple and beautiful things were and comparing it to our expectations, and we were very happy. We were very happy to find that the answer for G of t that we found decayed exponentially with time because that reflects thermalization. So it looks good, like it's accurately representing the quantum system that we thought the black hole might represent. This is a good thing. But there's a problem, which is that the correlator we computed, G of t, if you look at it as a function of time, it's obvious that it just continues decaying forever. And in fact, if we take t very large, it decays to 0. So as it turns out, this property is actually too much of a good thing. So decaying was a good thing, it represented thermalization, but this kind of very aggressive decay as time goes to infinity is too much of a good thing, and it's inconsistent with general properties of quantum mechanics. So let's see why. So I should have written this formula earlier, but this is what we have been computing from the perspective of the boundary theory. G of t is equal to trace e to the minus beta h times O of t, O of 0. O are some simple operators, simple quantum mechanical operators. So this is a 2-point function in the thermal state. And this is the quantity that we should compare our answer to. Now, if you take this and write it out in the energy eigenbasis by inserting a bunch of complete sets of states, then you find that this can be written as a double sum, a sum over 2 different sets of energy eigenstates labeled by m and n. And you have a square of the matrix element of the operator O. And then you have some factors that depend on the energies, E sub m and E sub n. So these factors depend on beta, and they also depend on time t. And the important thing to notice here is that as a function of the time t, this is a discrete sum of phases. As t changes, each of these terms just changes by a phase. So the magnitude of an individual term doesn't change, only its phase changes. And that turns out to mean that a function like this cannot go to 0. The closest it can come to going to 0 is to decrease for a while. rattle around, and then eventually recur. These functions like this are very interesting functions, discrete sums of phases. And mathematicians refer to functions like these as quasi-periodic functions, or almost periodic functions. What it means is if you wait long enough, then eventually these phases kind of realign, and the function has it's almost a periodic function. It comes back almost to the same value it was at t = 0. So in particular, it can't just decay forever. It has to have this interesting structure where eventually it comes back to a large value. So that's some very simple mathematical fact about functions like this. And it implies that the answer we found for g of t is wrong. It's not necessarily wrong, but it is incompatible with the claim that the black hole is secretly describing a strongly interacting quantum system. So I said before that it's very hard to compute this correlator for a strongly interacting quantum system, and that's true. But there's one general property of it that it's easy to discover, which is that it can't go to 0 at large time. And that's what we did here. We just observed that it can't go to 0, and that's a contradiction with the computation that we found. Okay, so there's a similar problem for the thermal partition function z of beta. In a quantum system, it's also just a discrete sum of exponentials e to the minus beta times e. And the function that we found, that e to the pi squared over beta, that function does not have this property. So these problems that we've been discussing, this tension between the gravity answers and the discrete sum of phases, which you expect from quantum mechanics, that problem is known as Maldasena's version of the black hole information problem. And it's a very deep problem, and it remains unresolved. We don't know what resolves this problem. What I'm going to do is try to explore the problem a little bit more, and we'll stay for the moment in the context of JT gravity. I think I'd actually better stop now. I don't want to, I want to have time for a couple more questions if there are any, and I don't want to rush through anything. So I'll just pick up here tomorrow and we'll discuss first steps towards trying to resolve this problem.
Okay. Yeah, you're going to mute yourself and send Douglas to stop. So there is a raised hand from Pedro Jorge Martinez. Yeah, please go ahead.
Hi, can you hear me? Yes.
Yes.
Okay, could you expand a little bit more? Why is it mandatory? I'm assuming that this last condition on the discrete sum requires, it's actually a requirement on the spectrum, that you have a discrete spectrum. Can you explain more why is it mandatory to have a discrete spectrum?
Okay, good. So there's two aspects to the answer to this, and I want to explain both of them. So the most straightforward answer is this. This black hole is supposed to be representing a quantum system with finite entropy. So the computation that we did of the partition function gave some finite answer. And the entropy that we computed was, again, it's some finite answer. So if a quantum system has finite entropy, then it cannot have a continuous spectrum. It has to have a discrete spectrum. So first we compute the partition function, we find the entropy is finite, and then we go and compute other things with the knowledge that we should be comparing it to something with finite entropy. And if the entropy is finite, then the spectrum of energy eigenstates has to be discrete. And then we run into this problem. Now the second way of answering your question, the second thing that I wanted to say is it's really just a second way of saying that same thing, but I think it's helpful. The rule for the partition function in a quantum system, whether the spectrum is continuous or discrete or whatever, is that you sum over all energy levels with weight 1. So let's imagine applying this formula to a system with a continuous spectrum. If you apply it to a case with a continuous spectrum, then you're still summing up every single energy eigenstate with weight 1. And that means that we get infinity times an integral. Normally an integral, it's a limit where you sum up a bunch of discrete things with very small weighting dx. But the rules of quantum mechanics say the partition function should be a sum over all of those discrete things with weight 1. So it's like you're doing an integral, but you forgot to insert the dx. And that means that the answer is infinite. So the proposed resolution that you were suggesting, that the spectrum should be continuous, would only be consistent with the case where the partition function is infinite. And actually, it would be a resolution in that case where the partition function is infinite. And we can discuss that a little bit more next time.
Okay, thank you.
Okay, there is also a question in the chat from Raghu Mahajan. Why is there a -I multiplying the sinh in the expression for g of t?
Okay, good. So let's go back to the Euclidean answer. The answer in Euclidean signature didn't have any funny i's or anything like that. It was just 1 over sine tau to some power. And tau is the imaginary part of the time. So in order to compute this, to convert this expression to real time, we need to convert this into t. So that means that we're supposed to set tau equals I times t. Okay, and if we set tau equals I times t, then I think we get this expression, although it's possible that we don't have the minus sign. Was the question about the I or the minus sign?
There's also a dt d tau to the delta from the transformation, so that I think cancels the i's.
No, we don't have a dt d tau.
Oh, you have a. Yeah, I was just thinking the answer has to be real. So in the end, there
the answer is not real. It's not real because these operators are separated in Lorentzian time, so they don't commute with each other. So it's not real.
Oh, okay. Thanks.
Yeah, I'm not positive if I put the minus sign correctly. I hope I did, but it's possible that I made a mistake. But in any case, there's an I here. Yeah, I think what Raghu was pointing out is it's a good point that the 2-point function of commuting Hermitian operators has to be real. That's an easy thing to prove in quantum mechanics in general. But here the operators are separated from each other in Lorentzian time, but they're kind of at the same point, so they don't commute with each other. And the fact that this 2-point function is complex means that they don't commute with each other.
Oh, there was a question from Human Yashat. Can you explain more this version of the information problem? I guess this means Maldacena version.
Can it explain more what? Sorry?
Can you explain more this version of the information problem?
Yeah, so, well, I put on the Slack channel, I put references, and one of the references is to Maldacena's paper on this. And I really recommend that you read that, especially the section that I pointed out. So he explains there a little bit more, but the problem is just that, okay, the problem is with 2 things. We are assuming, first of all, that the black hole behaves like an ordinary quantum system. Okay, and then we're supposed to check stuff. And this Maldacena's version of the black hole information problem is like a problem that is discovered in doing those checks. It's some kind of tension that we're finding, which suggests that our original answer was not right, or at least we need to include something else. So, okay, so what is the problem? The problem is the following. In a quantum mechanical system with finite entropy, this function, this 2-point function, cannot decay to 0 forever. It has to be an almost periodic function. It's a sum of phases, and so it cannot decay to 0. But the gravity computation we did found an answer that does decay to 0. So there's a tension between those 2 facts, and That tension is what goes by the name of Maldaceno's version of the black hole information problem. I'm not sure if I answered the question, but please please follow up. You can just unmute yourself and ask directly if you want to follow up on that.
Well, there are actually quite a few more questions in the chat. I don't know, but we are on the time limit. But if you want, we can continue for some time.
Well, it's up to you. I'm happy to keep going, but it's up to you.
Well, okay, we can try a few more questions. So there's a question from Ignacio Salazar. Is the tension between computing the correlator in the probe limit and considering the large M limit?
Ah, okay. This is a good guess. It's a good guess, but it's not, turns out not to be the case. And I'll explain tomorrow that you can compute it exactly and you still find a function that decays at late time.
And okay, the next question from Bruno Cornero. Building in Pedro's question, could you solve, in quotation marks, the problem by having a high density of levels at high energies? The partition sum would still be infinite in a sort of Hagedorn transition. Is this a way to understand the paradox?
Oh, well, but we computed the partition function and we found that it wasn't infinite. So you could say that the resolution of this is that really there's a continuous spectrum of energy levels. And then maybe you don't have a problem with the 2-point function anymore, but you have a huge problem with the computation of the partition function, which gave something finite. So either way, there's a problem.
And maybe the last question for today from okay, so no, there was a raised hand, but it disappeared. But I think I propose actually that the people ask, yeah, those who didn't have chance to get their question answered, they ask them again on Slack, because yeah, I propose we make a pause till the next till the next session.
Okay, yeah, I'll try to monitor the Slack and I'll try to answer questions there, or anybody else can also go ahead and answer them if they like.
Okay, and yeah, let's thank Douglas again.
Okay, thanks, thanks everyone,
and we'll have a 10-minute break till Atish's tutorial at 6:15.